everyone. I am Yun-Ju Song at Seoul National University. I'm going to be the chair of today's last session, Metals in Biology and Medicine. We have wonderful speakers, and there are some slight changes in the schedule, which will be addressed later on. Our first speaker of today's afternoon session, is Professor Youngmin Wang. Is he there? Oh, awesome. Yes.
Yeah.
All right.
So can you see in the PowerPoint?
We'll get to the point soon. I will give you an introduction first.
Okay. Yeah.
Okay. Professor Yun-Ming Wang did a PhD in 1990 and did a postdoc in Mass General Hospital. And he got an independent position in 2092. And then he now has been a professor in the Department of Biological Science and Technology, Institute of Molecular Medicine and Bioengineering, and National Youngmin You University. Okay, and today he's going to give us a story about fabrication of modified nickel form electrodes as biosensors. And let's see whether we can see your slide. Did you? Okay, we got your slide. It's a little bit truncated on the left side.
Yes.
We'll
Okay.
see. Okay.
Okay. So, okay, and thanks, Professor Song's and kind introduction. I also want to thank Professor Lan and Professor Lin and Professor Mihi Nim, and organize this nice symposium, and invite me and give me a chance to talk my recent work. Okay, so the title of my talk today is that is the fabrication of the MOF, modified nickel form electrode, as a biosensor for detect some kind of biomarker. Okay. And first, I just want to introduce some kind of biosensor. Sorry, wait. Wait. Okay, yeah. Okay, yeah. Okay, first, I want to introduce, how about biosensor? I think it's since, the 1960, right, they start to have some kind of biosensor. For example, and for the glucose biosensor, and piezoelectric biosensor, and optical biosensor, even they have 2000, they have a nano biosensor. Recently, right, and they just have some wearable biosensor. For example, that is for the tools, contact lens, and also use the sweat microfluid. So this is that is a wearable biosensor. Okay, and sorry. Okay, yeah. Okay, here I just try to tell you the design or fabrication some kind of a biosensor device. This column that is we call that is a target moiety, always used in the biosensor. For example, like antibody, enzyme, or aptamer. And also you need some kind of active material, like some kind of conductivity and polymer or nanocarbon. Okay, and also you need some substrate. For example, you can use the silk or plastic or paper. And then finally, you were sensing some kind of biomarker. Okay, in in our study, and just show in this cartoon, okay, and we just use the morph as an active material, and then we will just coding to some chips, and then we can detect some biomarker, use the small device. Okay. And here just to show you, the major component of a biosensor. Here I just mentioned some kind of analyzer that is a biomarker, and also you need some target moiety. For this study, we use the antibody, and some kind of transducer, and they have like an optical, thermal, piezoelectric, right? But for our study, we use the electrochemical analysis. So the come out of the signal that is impedance, that is charge transfer resistance. Okay, so the first biomarker I want to detect that is cardiac troponin I. Okay, and here we try to synthesize dimetal morph, and then we will sensing this biomarker. Okay, and first I will introduce what is the morph. Morph consists of the metal and organic ligand. So like this cartoon, yeah, and then you can make like a meta-organic framework. And the character of this morph, they have a larger surface area, highly and older micropole structure, and also have a high loading efficiency. So most of the morph always used in the drug carrier study. But for my study, we try to use for the sensing because we try to increase their sensitivity. Okay, and the substrate we use is the nickel foam, just like this one, and they have a high electrical conductivity and also have a high mechanical strength. And here, the first one I just introduced, like this biomarker and the cardiac troponin I. During the cardiac damage, right, the level of this biomarker is around 0.7 to 1.4 nanogram per ml. But normal it's less than 0.4 nanogram per ml. Okay, so we will use this strategy to synthesize our electron. And here is the morph, and we will introduce the amino group, and then they can conjugate with the antibody, and then we will use the BSA to deactivate the free amino group. So finally, we can sensing and antigen like troponin I. Okay, here that is immunosensor design and fabrication. Okay, so and in this autograph, right, and we will put like the nickel foam substrate, and the ligand we use is 2-amino phthalic acid, and they have an amino group, and then another one is ion and cobalt cluster. But we have to synthesize this cluster first, and then we just put all of this in this autograph. Inside have a Teflon container. Okay, so we use the hydrothermal synthesis, and so finally we can uniform grow the this morph and on the surface of the nickel foam. Yeah. Here, just to show the results of the morph, okay? And this is the SM image. This figure is a pure nickel foam, and after grow the morph on the surface of the this nickel form, we will get this same image. And then we just enlarge and this morph. And finally, we can get this this structure. So that is a nanosphere structure. Okay, and this one is just the TM image. Okay, and here we just want to do some kind of characterization. And this one that is we use the powder X-ray. This is a powder X-ray pattern, and also we use the XPS and the full survey. And we can get the all of the elements like the carbon, oxygen, hydrogen, ion, cobalt, and the ion and the cobalt layer ratio is about 2:1. Okay, and here we also use the high resolution XPS. Here is the ion and the cobalt spectra. From this spectra, we can see, and they are two ion 2p and binding energy. Okay, and is this two? The binding energy distance around 13.2, and they also have another satellite figure is 17.6. So from this result, we can confirm that is ion 3 or staging state. And this one is the cobalt. And for the cobalt, also they get the 2p peaks and also 2 satellite. And we can confirm that is cobalt 2 or staging state. We also use the DET and laminar motor to calculate their surface area. From this curve, we can find our morph. They will desorption and absorption the nitrogen repeatedly at the low pressure. So that means this morph belong to the microporous nature. Okay, and here we just calculate the pole size of the this morph, and that is 1.1 nanometer and 1.5 nanometer. Okay, and then we will use the electron chemical analyzer to measure their EIS. EIS is electron chemical impedance spectroscopy. Okay, so here just to show the Nyquist probes obtained from the EIS measurement. And so this one is just the nickel form alone. And the green one that is morph and coating on the surface of the nickel form. And from this curve, we can fit the electrical circuit, and then we can get the charge transfer resistance. And from this result, the resistance is quite low, just because we can, and because of the morph, they can catalyze the charge transfer process on the this redox probe. Okay, and then we just immobilize the conjugate with the antibody, and the resistance will be increased. And also conjugate with, deactivated with the VSA, the charge resistance also increase. Okay. And then next, we will do the concentration dependence study, and for the we use the antigen that is troponin I. So we can this is the Nyquist probes, and generated from I just mentioned is EIS measurement. Okay, and so increase the concentration of the troponin I antigen, right? So their charge transfer resistance will be increased. Okay, and from this curve we can calculate the detection limit is around 13 femtogram per mil. That means the sensitivity is quite high. And this is in PBS buffer solution. And then we try to simulate for the blood and the sample, right? So we measure this one in 10% serine solution. And we also get the detection limit is about around 13 femtogram. Okay, so both of them is similar. And we also measure the cyclic watermetric, and the concentration of the antigen troponin I increase, and then their peak current will be decreased. Okay, this one we also study their specific study. Only the biomarker and the troponin I, they can increase the charge transfer resistance. The other biomarker, like troponin T, FSH, and they cannot increase the charge transfer resistance. The last one, we will try to study their reproducibility. So we just use 3 batch of the MOF we synthesize, and then measure 2 concentration. One is 10 nanogram per ml, another one is 5 nanogram per ml. So the result is similar. So that means, and for this the sensor, right, their reproducibility is quite high. So finally, we can get this conclusion. And detection limit is low, it's quite low, and also they have a high specificity. So maybe this biomarker have a potential alternative and use for the troponin I detection. Okay, this is the first topic I want to talk. The second one, the biomarker I want to sense that is follicle stimulating hormone. Yeah, and this curve just show, and this is the age of the women. Okay, so there are 2 hormone. One is the LOH, another one is I just mentioned, and FSH. After 15 years old, and the FSH level will be increased. So this FS maybe can use as a biomarker for the menopause. Okay, and in our lab we have been used the silicon nanowire to sense this biomarker. And the strategy is like this one, because this is the folic acid terminal. They have a sialic acid. From the literature survey, we can find the sialic acid. They can bind in to the borononic acid. So that is fine. We will use this protocol, and this is the silicon nanowire, and we will modify and use the silane boronic ester, so we can so they can get this compound. Finally, use the sodium iodide, so we can get this boronic acid. So we will use the nanowire and microfluidic to treat the sample. Finally, we can also get the for this study, we just measure their current. So the detection limit is around 0.72 femtomolar, and this is in the serum. So it's 1.1 femtomolar. So the results is similar. Also, we will study their selectivity. Only the FSH can increase their current. So we can use like this nanowire as a sensor to sense this biomarker. But right now, we try to also use the MOF to sense this biomarker. And the MOF we use, and the substrate, we also use the nickel foam. but we will use another mode to sense this biomarker. Okay, and first of all, we have surveyed the paper, and have been in the CanCom. They have been synthesized this MOF like this MOF 101, but that is the chromium, and this kind of the MOF that can high specificity and efficient enrichment of the glycopeptide. So, and because I just mentioned this FS is a glycoprotein, so and we try to use this MOF, but and we don't use this chromium. We use the ion because ion is more biocompatible. Okay, so here just to show the scheme, we synthesize our MOF on the surface of the nickel foam. The ligand we use is the same, and we only use the iron chloride and nickel foam. Put all of this in this autoclave, and then we use the hydrothermal synthesis. And also we will conjugate with the antibody and use with the BSA to deactivate the free amino group. So finally we can sense this and FSH antigen. Okay, here just to show the MOF we obtained. Okay, here is a pure nickel foam, and here is a MOF grown on the surface of the nickel foam, and then we enlarge of this SM image, so we can find that is a narrow sheet that growed on the nickel foam. And we also measure layer size. The average of the this sheet, right, is around 25 nanometer. Okay, and we also use EDEX to analyze and all of the elements that have carbon, oxygen, nitrogen, ion, and nickel. And here just to show the percentage of each element. Here, this slide shows the TM image of this MOF. Okay, yeah, and so and the size and that is looks like it's a hexagonal micro spindle structure, and the size is around 200 nanometer. Okay, and here I just want to characterize this MOF, and this figure that is use the FTIR. Okay, so from the FTIR we can get that they have some functional group like an amino group and some functional group in this MOF. And this figure that is polar X-ray pattern. Okay, it's this pattern. Yeah. And also we use the XPS, and here just show the full range of the XPS. Okay, and then here's carbon, oxygen, and ion. This table just show all the binding energy for some chemical state. And for the ion, right? And they are two. 2p and 2p. One is 209, another one is 722. The difference is around 13. Is similar to the previous one, and also they have a satellite. The binding energy is 714. So this result is similar to the previous one, and so we can confirm that is ion 3. And here also show we use the nitrogen gas desorption and absorption and desorption, and this is the curve we get. And we also can calculate their surface area, and it's around 1,752. So this surface area is significantly higher than the previous one. So hopefully we can increase their sensitivity. We also calculated their pore size is around 2.3 nanometer. Okay, and here that is a cyclic watermetric measurement, and the red color that is morph coating on the surface of the nickel foam. And we can find that the peak current is quite high. I think the reason is morph they can catalyze the charge transfer and process for this probe. After you conjure with the antibody and treat with the antigen FSH, the peak current will be decreased because they have a stronger interaction. We also try to quantify how much of the antibody and conjugate with this morph. From this curve, we can calculate that absorbed antigen concentration is around 4.8 microgram per ml. Okay. And here, this slide just to show we use the electron analyzer to measure their EIS. Okay, and here is the concentration dependence study. Okay, from this data, we can fit the charge transfer resistance. The charge transfer resistance increase with increase the concentration of the antigen FSH. Okay, and this study in the PBS buffer solution, and we can calculate there, and the detection limit is around 11.6 femtogram per ml. And this one is in the serum, 10% serum, just to try to simulate the blood sample. So the result is similar, is around 11.5 femtogram per ml. So we can find that this sensitivity is quite high. Detection meter is very low. Okay. And here, this table just to show this work compared with the other paper published before. So the detection limit is very low for our study. And we also try to check their morphology for our morph. This is the pure nickel foam, and this is coating the morph. And this one is conjugate with the antibody, and the last one is treated with the antigen and biomarker FSH. So we can find their morphology is a significant change. We also use the confocal to prove our antibody conjugate with the morph. Okay, here is just the morph and treated with the rotamine dye, and this is the antibody and conjugate with the morph, and that is bright field, and then we merge together, and we can find the bright one. That is the antibody. Also, and we will study their selectivity. Okay, so only the FSH they can increase the charge transfer and resistance, and the other biomarker like the TSH, LOH is another biomarker of the menopause, but only the FS that can increase the charge transfer resistance. The last one is we also did their reproducibility study. Use the 3 different batch and detect 2 different concentration of FSH. One is the 10 nanogram per ml and 10 femtogram per ml. The results is similar. So the reproducibility is very high. Okay, and we also try to study their stability. Okay, if we in the pH equal 4 and equal 10, and the morphology is similar, so it's very stable in acid and base condition. And we also, study their mechanical stability, and we just put the morph in sonication. And this is the morph alone or conjugate with the antibody. And the morphology is similar, so mechanical is stable. The final one, and I just mentioned, we try to use the small device. But here we don't use the nickel foam, and we use the gold chip. And the gold chip, first, we should be, use the MUA, and they have style, they can conjugate with to binding to the gold chip. And then we will just use the morph we synthesize, and we will bind into this conjugate with this morph, and then use the ETC NGS to bind in the antibody, and also use BSA to block it. Finally, we can try to use this device to sensing this biomarker FSH. Okay, here just show results, and that is a concentration dependence study, and we can measure their EIS. And from this is in PBS buffer solution, and from this curve we can calculate their detection limit is about 7.2 femtogram per ml. And this value a little bit and lower than the previous one. Previous is around 11. This one is about 6. Okay, so that means small device, and the detection limit is quite low. Okay. Another one is we also try to simulate the blood sample. So this study is prepared a sample in the 10% serum, and we use this device to measure their EIS. Okay, so from this curve, we also can calculate the detection limit for this small device. It's around 7.225 femtogram per ml. So it's also similar with the results in the PBS buffer solution. Okay, so finally we can get this conclusion, and we just in situ and grow this morph on the surface of this nickel foam. Okay, and then we contribute with the antibody, and then we can detect the antigen FSH. And if we use the electrochemical analyzer, right, the detection limit for buffer solution and serum is around 11. But we use the small device, the detection limit is around 6.2. It's a little bit lower than that one. Okay, so okay, then finally I want to send the grant from the Taiwan MOST, and also my collaborator Professor Lu and Professor Yuan, and the device I cooperate with Professor Chen, and also sends my student. And thank you for you listening. Thank you. Yeah.
Okay, thank you. If you have any questions, welcome to join. While we are waiting for any questions, I have 2 quick questions actually. So first is, do you think that the antibodies, the amino groups are utilized to put the antibody on the surface of the mouth, right? So yes. Do you envision how much of antibodies are placed in mouth? So what is the ratio between the number of the antibody per amino group available in mouth?
Oh, I just give you the results. How much amount of the antibody we coating on the mouth, right? Mm-hmm. But we didn't calculate their ratio. Mm-hmm. But we have major how much of the concentration of the MOF on the surface, on the surface. Yeah.
I see. So do you envision that those antibodies are only placed only on the surface of the mouth, or some of them can get into the like micropores? Like how
Maybe, yeah. They also they can go to like in the pole, in the pole. Okay.
I see.
Yes.
I see. Okay. And second question is, let's see. So your sensor shows a very low detection limits, which is it's incredible given that you give us a lot of high sensitivity. But is the concentration level that you mentioned is more like physiologically relevant?
It's and small device is around 6, right? And then, but if we use the electron chemical analyzer, that machine, right? It's around 11. Yeah, but I think this detection limit is quite low. So we can measure in the future we can measure for the real sample. Yeah. Okay.
I see. Thank you. With no further questions, let's thank him again for a great talk.
Okay. Thank you.
Thank you. She is a student in Lanjana Gupta. She is a student at the Department of Chemistry and Nanoscience at Ewha Women's University, and probably in Wanu Nam's group. And she will tell us about heme copper 2 model chemistry. Please.
Thank you, Professor Song, for your kind introduction. So, my name is Ranjana Gupta, and I am from Professor Wanu Nam's lab. So today I am going to present on the topic heme compound 2 models in chemoselectivity and disproportionation reaction. So before I begin with my presentation, let us see some of the introduction part. So this is the well-known catalytic cycle of cytochrome P450, wherein the catalytic cycle starts with the resting state of iron 3. The water molecule is bound axial to the cis ligand, cysteine ligand at the 6th binding site of the iron center, and upon the water molecule is released when the substrate molecule enters the binding site, and reduction of ferric to ferrous takes place. Upon O2 binding, upon O2 binding, we get the iron superoxo complex, which on further reduction and protonation leads to formation of iron 3 hydroperoxo species, which is known as compound 1. So this compound 1 on further protonation and this compound 0 on further protonation and O bond heterolysis cleavage leads to the formation of iron 4 oxoporphyrin pi-cation radical species, which is also known as compound 1. And this compound 1 is highly reactive, and it is well characterized in literature, and their oxidation reactions have been studied. Further, hydrogen abstraction leads to the formation of iron 4 oxo species, which is known as compound 2, and this So this compound 2 is not so intensively studied due to its lower oxidation property as compared to compound 1, and it is not considered to be the true active oxidant, resulting in oxidation reactions. Further, oxygen transfer from this iron oxo leads to oxygenation of the substrate, leading to formation of products, and dissociation of these products completes the catalytic cycle. So in biomimetic chemistry, various metal oxygen intermediates have been already studied by various groups, and the first synthetically synthesized iron 4 oxoporphyrin compound 1 and compound 2 species has been reported by Professor Gross in 1981 and co-workers, and they observed that upon addition of MCPBA to the starting iron porphyrin complex leads to formation of the green species, and this was further characterized with various spectroscopic techniques to be compound 1. Similarly, addition of PHIO to the starting iron porphyrin complex leads to formation of the iron oxo species, which is known as compound 2, and it was also very well characterized. Later, in 2003, the first crystal structure of iron 4 oxo, iron 4 non-heme iron 4 oxo was reported by Professor Nam and co-workers. Later, several reactivity studies have been performed to understand the mechanistic aspects of compound 1 and non-heme iron oxo species. So, for example, here they have studied the effect of substituents on the reactivity of compound 1 species, and also axial ligand effect has been studied. And also many mechanistic studies have been carried out to study the oxidation of different variety of substrates by non-heme iron oxo species. And the reactivity of non-heme iron oxo and compound 1 studies have been compared. For example, the chemoselectivity of cyclohexene oxidation by non-heme iron 4 oxo and compound 1 model complexes has been studied in various oxidation reactions. However, no one till date have studied the effect of compound 2 and the effect of the axial ligand or the effect of substituents on the reactivities of substrates. So, we decided to study the reactivity of compound 2 using cyclohexene as the probe and also to compare its reactivity with non-heme iron oxo and compound 1 species. So, for our studies, we have used two kinds of iron compound 2 unit compound 2 supported by different ligands. One with the 1A is with the pentafluorinated porphyrin ligand, and 2A is with the electron donating mesitile group. So let us first see the characterization of 1A. Here, upon addition of PHIO to the starting lead to formation of absorption bed at 545 nanometer corresponding to the formation of compound 2 species, which was characterized with various spectroscopic techniques. So in positive mode CSI mass, we observed a prominent peak at 1108, which we observed a 2 mass unit shift upon O18 labeling experiments. Then EPR shows a silent signal indicating for the oxidation state of iron to be +4. Then later we checked the Raman of the compound 2 species, and we observed isotopically sensitive band at 828 centimeter inverse, which shifted to 720. And we observed a Raman shift of 36 centimeter inverse, which is well matching with the calculated Raman shift of 37 centimeter inverse for iron oxo unit. Further, XS shows increase in energy from 7123 to 7124.3 electron volt, indicating increase in oxidation state from plus iron 3 to iron 4. And we also observed increase in intensity in the pre-edge region, confirming the smaller iron oxo bond. Then we obtained the iron oxygen bond distance of 1.65 angstrom and iron chlorine bond distance of 2.2 angstrom. Further, we characterized intermediate 2A, which is supported by electron-rich porphyrin ligand, and we observed absorption band at 545 nanometer, and then EPR shows silent signal indicating iron oxidation state of iron to be +4, and resonance Raman shows Raman shift of 37 inverse, which is matching well with the calculated Raman shift of 37 inverse, indicating that we have successfully generated compound 2 species supported by electron-rich and electron-deficient porphyrin ligands. Further, we studied the oxidation of cyclohexene by these two compound 2 intermediates. So first we studied, we added addition of cyclohexene to the compound 2, 1A resulted in decay of peak at 545 nanometer peak absorbance, and we observed that the decay rate followed first order kinetics, and upon increasing the concentration of cyclohexene, the rate increased, affording the K2 of 6.1 into 10 to power minus 3, and we observed a KI of 41. Product analysis, EPR product analysis by EPR of the inorganic showed formation of iron 3 species, and GC product analysis by GC and GC must revealed formation of cyclohexenol product. Further, on addition of cyclohexene to the intermediate 2A lead to the decay of peak at 545 nanometer with concurrent formation of peak at 501. However, here interestingly, the decay rate obeyed second order kinetics, and upon increasing the concentration of cyclohexene, the rate increased and reached a saturation at higher concentration of cyclohexene. Then product analysis revealed formation of iron 3, and organic product analysis revealed formation of cyclohexene oxide product. This is very interesting because the compound 2 supported by electron deficient porphyrin leads to the formation of cyclohexenol product. However, in case of compound 2 supported by electron rich porphyrin leads to formation of epoxide product. So why this phenomenon is occurring, that is reactivity of 1A shows first order kinetics while this 2A shows second order kinetics. Then we see a linear correlation in case of 1A while saturation behavior in case of 2A. Also cyclohexenol product and KI of 41 in case of 1A, and cyclohexene oxide product with KI of 1. So this can be explained using disproportionation in case of 2A leading to the formation of compound 1 which is 2B and iron 3, and this compound 1 then further reacts with cyclohexene to give the cyclohexene oxide product. And we obtained this equation from this scheme, and we obtained a linear relation when we plotted the plotted K observed inverse versus cyclohexene inverse concentration, and we obtained the rate of disproportionation to be 1.9 into 10 to power 2, giving KI of 1, which is further supporting that disproportionation of compound 2 in case of 2A takes place to compound 1, and then compound 1 reacts with cyclohexene to give epoxide product, which is already reported by compound 1 species. Further, to prove that disproportionation of 2A takes place while not in case of 1A, we independently studied reactivity of cyclohexene in compound 1 species. So upon addition of MCPBA to the starting iron TPFPP, we observed a peak at 660 nanometer, which is characteristic band for compound 1 species, and on addition of cyclohexene, we observed a decay, and the KI was obtained to be 1. So this proves that in case of 1A, compound 2 is the active oxidant reacting with cyclohexene to cyclohexenol product, while in case of compound 2, it reacts with cyclohexene to give cyclohexene oxide product. Hence, disproportionation is not taking place in case of intermediate 1A. Later, upon addition of MCPBA to the starting iron TMP chloride supported by electron-rich porphyrin lead to formation of peak at 666 nanometer, which is corresponding to the compound 1 species. And upon addition of cyclohexene, the peak corresponding to compound 1 decayed with formation of peak at 505 corresponding to the starting iron 3. Here, interestingly, we obtained a KI of 1 and a cyclohexene oxide product. This proves that in case of compound 2 supported by electron-rich porphyrin, we observed that cyclohexene oxide was the product, further proving that disproportionation of compound 2 to compound 1 takes place, and we get cyclohexene oxide product. Further, to support disproportionation in case of 2A and not in 1A, we studied effect of acid and base on the reactivity of cyclohexene by compound 2 species. So upon addition of cyclohexene to the compound compound 2 1A in presence of acid, we did not observe any enhancement in reactivity of cyclohexene. While in case of 2A, when we added when we added acid with increasing concentration of acid, the rate increased, giving a linear plot. And in presence of and when we added base to the intermediate 2A, we observed slow reactivity in case of 2A, and also interestingly here now the decay rate observed followed first order kinetics and not the second order kinetics, further proving that disproportionation of compound 2A to the corresponding compound 1 takes place, and compound 1 is the true active oxidant reacting with cyclohexene to give the further cyclohexene oxide product in case of intermediate 2A. So also we have performed DFT calculations. However, due to lack of time, I could not cover that here. So to conclude, we have synthesized two compound 2 with supported by electron deficient and electron rich porphyrin ligands, and then we have also investigated their reactivity in cyclohexene oxidation, and we observed that in case of compound 2 supported by electron deficient porphyrin, cyclohexenol product was obtained with KI of large KI of 41, and in case of compound 2 supported by electron rich porphyrin ligand, we observed KI of 1 and cyclohexene oxide product. Further, this can be explained on the basis of disproportionation in case of 2A to give corresponding compound 1 and iron 3, and now this compound 1 reacts with cyclohexene to give the oxygenated cyclohexene oxide product. Also, DFT suggests calculations confirm that compound 2 models prefer CH bond hydroxylation, and that disproportionation of compound 2 models can be controlled thermodynamically by the porphyrin ligands. Reactions of 2A with cyclohexene acid and base effect, and altogether confirms that disproportionation is occurring in case of compound 2 supported by electron rich porphyrin ligand. So at the end, I would like to thank my advisor, Professor Nam, Professor Fukuzumi, Professor Lee, Professor Cho, Professor So, and all the CDC group members for their kind help and support. Thank you very much.
Okay. Thank you. Is there any questions? Okay, I have a quick one. So based on your study, if you change the electronic structure of the porphyrin, basically you bifurcated reaction pathways.
Yes.
What happens if you use the one in the middle? Do you see the mixture of those two products?
Actually, we have tried with TDF-PP. However, in that case, we observed cyclohexenol product, but we did not include it here.
I see. But not the epoxide.
We did not use other electron-rich porphyrins, so we just have the two.
All right. Okay. Thank you. All right. Let's thank her again. And today's last speaker before the coffee break would be Professor Tsai-Te Lu or Shan Lu. Are you there? Oh, there you go. All right. Hey, I will give a quick introduction. He received PhD in 2009 at National Tsinghua University in Taiwan, and he did a postdoc at MIT, and then he started his independent career in 2013, and now a associate professor in National Tsinghua University in Taiwan. And today he's gonna tell us about nitric oxide chemistry. All right, so yours.
Okay, so thank you, Yun-Ju. So can you all hear me?
I can hear you, but I cannot see your slide yet. Oh, yes, it's ready. Okay. So yeah, you can go ahead.
Okay, thank you, Yun-Ju, again, for the introduction. And also I'd like to acknowledge the organization committees, especially Professor Nam, Mihi, and SJ for the consecutive invitation. and organization of this hybrid waste symposium during this pandemic situation. As in these metals in biology and medicine section, today I would like to focus on our continued journey on bioinorganic engineering of natural dinitrosyl unit, during which we discovered that the metal-ligand cooperation effect in dinuclear dinitrosyl complexes occurs to facilitate the controlled delivery of NO. And before the end of my talk, I would also briefly share our recent discovery of metal-ligand cooperation effect in another type of dinucleotinics for small molecule activation. So in the recent years, our focus on the translational application of NO as a novel and effective biomedicine is inspired by its ubiquitous physiological function, which is dependent on its location and concentration. To translate these physiological functions of NO into the development of novel therapeutic approaches against the diseases or complications as shown here. However, the bottleneck and unmet needs for this translational application include first, design and development of a prodrug for the stabilization of NO regarding its short half-life within seconds under biological system. Second, this prodrug needs to achieve a spatial dosage and temporal control on the delivery of NO in order to regulate the location and concentration dependent physiology. Considering that all the NO-responsive targets are located in the intracellular compartments, in an ideal manner, cell-penetrating delivery and enhanced intracellular release of NO by the developed prodrug hold the potential to maximize the efficacy on regulation of NO-related physiology, and meanwhile, to minimize the side effect of NO outside of the cells. On the other hand, elevated level of extracellular reactive oxygen species under pathological condition was reported to promote the formation of cytotoxic and pro-inflammatory peroxynitride, NO2 radical, and hydroxyl radical. As a consequence, a prodrug for hours resistant delivery of NO also awaits to be further explored. As inspired by the natural utilization of dinitrosyl unit for the storage and transport of NO in our lab, we take this natural metallic cofactor as a starting point to build up a chemical library of biomimetic dinics for controlled delivery of NO. Based on the investigation performed in our lab, at the moment, this type of old but effective dinic features the most potential for biomedical applications. In addition to the naked dinics, functional conjugation of dinics with drug delivery systems, including endogenous protein vehicles or alternative biomaterials, further boost the controlled delivery of NO. Through activation of NO-related physiological functions, bioinorganic engineering of dinics and their functional conjugates holds the potential to develop a variety of novel therapeutic approaches. In the following slides, I will show you the consistent reactivities of dinics under biomimetic conditions and biological systems, which are followed by several examples about the biomedical applications of naked dinics as well as their functional conjugates. During the JB&U International Online Symposium in the last year, we discussed how the metal-ligand cooperation between the soft dinitrosyl unit and bridging thiolate ligand enables the reversible binding between thiolate bridge dinucleotinics and protein-derived cysteine residues, which was evidenced by the distinctive EPR feature of protein-bound mononucleotinic at G average equals to 2.03. So this work was mainly achieved by this young talent, Mr. Yida Huang. So in particular, he identified the cysteine 34 as the active site in BSA for binding of dinitrosyl unit based on the NEA modification experiment. Moreover, conversion of dinic 1 into BSA bound dinic initiates the accelerated release of NO under aerobic condition. On the other hand, rapid and reversible binding of dinic 1 toward gastrointestinal mucin provides an stabilization effect on dinic under the aesthetic environment in the stomach, as described below. So upon oral administration of dinic 1 to mice, rapid binding of dinic toward the gastrointestinal mucin enables the mucus layer as an endogenous reservoir for protection and stabilization of dinic in the stomach, which reflects on an in vivo half-life of around 2.7 hours in the stomach. This in vivo half-life of DNIC in the stomach is much longer than the in vitro half-life of DNIC in the simulated gastric fluid. So with regard to the reversible binding of DNICs toward the protein-derived cysteine residues, we further investigate that how this interaction can regulate the cellular uptake of DNICs. So under a simplified consideration of cells, we have extracellular environment and intracellular compartment separated by cell membrane, whereas we have to be aware of different organelles inside the cells. So based on the concentration of BSA in the extracellular environment and concentration of total proteins in the intracellular compartment, phthalate bridge dinucleotide DNIC dominates in this equilibrium under cell culture media with 10% of FBS, while protein-bound DNIC is the dominant species inside the cell. In addition to the equilibrium modulated by the concentration of cysteine-containing proteins and the side chain of bridging phthalate ligands, the kinetics for binding of different DNIC1 toward BSA were further studied. As opposed to the rapid binding and fast equilibrium displayed by reactions between BSA and DNIC1-OH, 1-TG, and 1-COONE, DNIC1-COOH features a delayed kinetics for binding toward BSA. So regarding this distinctive binding kinetics, DNIC1-COONE and DNIC1-COOH were further utilized to explore the mechanism for cellular uptake of DNICs. 4 different kinds of cell lines were utilized in the attempt to explore the potentially shared mechanisms for cellular uptake of DNICs. Upon addition of these 2 DNIC1 to different types of cells, based on the whole cell EPR study, cellular uptake of intact DNICs followed by intracellular conversion into protein-bound DNIC was evidenced by the identical EPR signals. There is a spin quantitation of the time-dependent change of these EPR signals for intracellular protein-bound DNICs. Treatment of dinuclear DNIC1-COONE results in an instantaneous formation of intracellular protein-bound DNIC with a Tmax at 0.5 hour, which is followed by its rapid decomposition. In contrast, a delayed kinetics for the formation and degradation of intracellular protein-bound DNIC with a Tmax ranging from 2 to 3 hours is observed upon addition of dinuclear DNIC1-COOH. This distinctive kinetics for cellular uptake of DNIC1-COONE and DNIC1-COOH respectively are consistent with those for their binding toward BSA. So based on the in vitro EPR study, thiol-mediated transport is proposed as the mechanism for cellular uptake of DNIC1 shared by different types of cells. So presumably, reversible binding of phthalate bridge dinucleotide DNICs toward protein-derived cysteine residues on the surface of the cell membrane may promote the cellular uptake and internalization of DNICs followed by intracellular conversion into protein-bound DNICs. In the near future, continued investigations using thiol-blocking reagent will be performed in order to support this proposed thiol-mediated uptake of DNICs. So after formation of protein-bound DNICs, intracellular release of NO were further evidenced by the fluorescence probe DAF-FM. Moreover, the distinctive kinetics for cellular uptake of DNIC1-COONE versus DNIC1-COOH are correlated with the first release of high concentration of NO from DNIC1-COONE and steady release of relatively lower concentration of NO from DNIC1-COOH. So relying on this distinctive NO delivery kinetics, DNIC1-COOH in comparison with DNIC1-COOH in comparison with DNIC1-COONE displays a higher biocompatibility against these different types of cells. So due to the proliferative effect of NO, controlled delivery of NO using DNIC1-COOH reflects on a wide spectrum cell proliferation effect on a variety of cell lines, which highlights the potential of biomimetic DNIC1 as a chemical biology tool to translate the physiology of NO into a regenerative medicine. So one step forward, we also attempted to explore the metal-ligand cooperation effect on reactivity of dinuclear DNICs under the simulated inflammatory condition. So under physiologic condition with low concentration of superoxide maintained by superoxide dismutase, Biosynthesis of low concentration of NO is followed by its dominant interaction with NO-responsive target to achieve the regulatory function of NO. Under inflammation, in contrast, both NO and superoxide with elevated level overwhelm the capability of NO-responsive target and SOD and promote the formation of peroxynitride, hydroxyl radical, and NO2 radical, which results in a vicious cycle on the pro-inflammatory condition. On the other hand, based on the biomimetic study, mononitrosyl metal complexes and TMEDA bound DINIC were reported to react with superoxide or dioxygen, yielding hydroxyl and NO2 radicals via the formation of metal bound peroxynitride as a transient intermediate. Of interest, after oxygenation of PNDDA bound DINIC, chelating nature of tridentate PNDDA ligand presumably triggers the intramolecular reaction between iron-bound NO and peroxynitride, leading to the ultimate formation of bis-nitrile ion complex without transient formation of hydroxyl and NO2 radicals. Inspired by the distinctive reactivity of DINICs toward dioxygen, we further explored the reaction between superoxide and dinuclear DINICs with bridging pyrazolate and thiolate ligands respectively. So upon titration of DINIC-2-ME with potassium superoxide, formation of pentanuclear DINIC is evidenced by IR and single crystal X-ray diffraction study, whereas characterization of its electronic structure using different spectroscopic tools was performed by beyond our discussion here. Of interest, a company generation of nitride captured by the potassium 18-quant fixed ether calcium is observed in the crystal structure. Through additional treatment of potassium superoxide, disappearance of INU NO absorption peaks is derived from the assembly of insoluble ADA consisting of ferric ion, methylpyrazolate, and nitride, which were categorized by ion KHXAS, MNR, and grease assay respectively. When DTBP is used as trapping reagent of importance, absent formation of hydroxyl and NO2 radicals is observed during this superoxide-mediated monooxygenation of pyrazolate bridge dinuclear DINICs. Despite the superoxide-mediated conversion of NO into nitride, low-temperature UV-Vis experiments were attempted, but failed to identify the transient formation of iron-bound peroxynitride. As opposed to the pyrazolate bridge dinuclear DINIC, reaction of thiolate bridge dinuclear DINIC with potassium superoxide promotes its partial conversion into the 1-electron reduction product, whereas the accompanying generation of dioxygen gas is evidenced by the GC. Upon subsequent removal of generated dioxygen gas through purging the solution with dinitrogen gas, stoichiometric formation of reduced DINIC demonstrate the superoxide dismutase-like activity of thiolate bridge DINIC and implicates an equilibrium between DINIC-1 and its reduced form enabled by redox interconversion of dioxygen and superoxide. So in a reverse manner, injection of dioxygen gas into the THF solution of reduced DINIC results in the partial formation of original thiolate bridge DINIC and superoxide, which is validated using MD chloride as a trapping reagent for superoxide. Based on this study, we explored the NO monooxygenation and SOD-like activity of dinuclear DINICs modulated by supporting ligands. Presumably, metal ligand cooperation effect in the covalent diion dithiolate core and in the redox active dinitrosyl ion unit plays a critical role to enable the SOD-like activity of thiolate bridge dinuclear DINIC. With its intact structure retained under the presence of superoxide. Moreover, this SOD-like activity of DINIC-1 may project on its in vitro and in vivo anti-inflammation effect described below. So according to the metal ligand cooperation in thiolate bridge dinuclear DINIC described above, now we have a better understanding about the mechanisms of DINIC-1 for oral delivery of NO to brain and for therapeutic efficacy against neurodegenerative disorders. So first, rapid and reversible binding of DINIC-1 to endogenous protein vehicles such as gastrointestinal mucin and serum albumin facilitates the oral to brain delivery of DINIC. Second, thiol-mediated uptake of DINIC followed by intracellular formation of protein-bound DINIC and subsequent release of NO promotes the proliferation of neuroprogenitor cells, which reflects on the in vivo hippocampal neurogenesis. Third, ROS-resistant nature of thiolate bridge technique rationalizes its anti-inflammation effect against activated microglia cells. So finally, these properties of TNIC1 enabled by metal ligand cooperation effect is translated to its therapeutic effect on recovery of impaired cognitive ability of aging mice with metabolic syndrome. So relying on the wide spectrum cell proliferation effect of TNIC1, moreover, translational development and application of unknown delivery techniques as a regenerative medicine were also explored for angiogenesis and diabetic wound healing, osteogenesis and bone tissue engineering, heart regeneration and cryoinjury, and skin regeneration. So we also investigated the application of TNIC1 to cell therapy. Recently, cell therapy has emerged as a potential strategy for clinical application to tissue engineering and regeneration, as well as the treatment of ischemic stroke and other complications. In particular, the therapeutic efficacy of cell therapy depends on the survival rate of post-engrafted cells, which encounter with a local environment featuring high oxidative stress, inflammation, and ischemia. So in this study, pretreatment of TNIC1 to mesenchymal stem cells, CBMSC, was explored in the attempt to enhance the cell viability of post-engrafted CBMSC. Despite the absent proliferation of TNIC1 on CBMSC, based on the microarray, qPCR, and Western blot analysis, moreover, treatment of TNIC1 can selectively activate the antioxidant and cell protective heme oxygenase 1. Of interest, the superior activation of HO1 by TNIC1-COOH in comparison with TNIC1-COOMe, presumably, is ascribed to its higher biocompatibility and steady release of low concentration of NO in the intracellular compartment, as described above. Through utilization of high concentration of hydrogen peroxide to mimic the high oxidative stress local environment, the TNIC prime CBMSC display and enhance cell viability. So one step forward, the mice with ischemic stroke were further adopted as the in vivo model to demonstrate the effect of TNIC1 on promoting the cell viability of post-engrafted CBMSC. After treatment of TNIC prime CBMSC to the brain of the mice with ischemic stroke for 4 and 7 days, the iris imaging results shown here support the enhanced post-engrafted cell viability of TNIC prime CBMSC. That is, pretreatment of TNIC1 modulates HO1-mediated antioxidant response and improves survival rate of post-engrafted CBMSC. So after investigations on a variety of unknown-related regulatory functions triggered upon direct interaction of biomimetic techniques with alternative types of cells. In the following slides, I would like to share several more examples with you to highlight how the drug delivery systems can serve as a booster to strengthen the efficacy of unknown delivery techniques. In the attempt to explore a prodrug of NO with enhanced overall bioavailability, in this work, the carboxylic acid group in TNIC1-COOH was utilized to facilitate its conjugation with metal organic framework, leading to the assembly of TNIC and MOF microrod through and post-synthetic acid-base reaction mechanism. Based on the pH titration experiments, protonation of the bridging benzene dicarboxylate linker in TNIC and MOF at a pH lower than 4 promotes its structural transformation into TNIC-T-MOF for protection of encapsulated TNIC1-COOH under acidic environment. Subsequent incubation of TNIC-T-MOF under stimulated intestinal fluid at pH 6.8 triggers the release of intact TNIC1-COOH, which reflects on a protection efficiency of 40 and 20%. This pH-dependent transformation of TNIC and MOF into TNIC-T-MOF, followed by release of TNIC1-COOH in a stepwise manner, moreover, project on the enhanced NO bioavailability upon oral administration of TNIC and MOF in comparison with free TNIC1-COOH and TNIC1-OH, which further reflects on its effective and chronic reduction of blood pressure in spontaneously hypertensive rat. Inspired by the dose-dependent anti-angiogenesis versus pro-angiogenesis effects regulated by biomimetic technique 1. Previously, we adopted the solid PLGA nanosphere as an artificial chaperone material for encapsulation and delivery of DNIC, whereas the assembled nanonode features elongated circulation in the blood circulation system and enhanced accumulation in the liver tumor. Relying on this improved pharmacokinetics and enhanced accumulation, upon IV injection of high dose of nanonode, the anti-angiogenesis effect induced by the high concentration of NO reduced the number of blood vessels in the tumor area. Of interest, low dose of nanonode promotes the pro-angiogenesis effect, triggers the tumor vessel normalization, and potentiates the anti-cancer therapeutic efficacy of low molecular weight doxorubicin, protein drug trail, and immunotherapy. So with regard to the effective regulation of tumor vessel normalization by nanonode, we further designed a stroma targeting NO delivery nanogel to reverse the pancreatic desmoplasia and to overcome the drug-resistant pancreatic tumor. Activated pancreatic stellate cell is a kind of fibrotic cells which participates in the fibrosis and build up a stroma in the pancreatic tumor, which further retards the chemotherapeutic efficacy of most of the anti-cancer drugs. Upon treatment of free DNIC1 to activated PSC, downregulation of profibrosis demonstrates the transformation of activated PSC into a quiescent state. That is, a no delivery DNIC1 holds the potential to reprogram the desmoplasia stroma in pancreatic tumors. Before the in vivo study, phase display study was performed to identify a novel stroma targeting LQT peptide, which was conjugated onto the surface of a nanogel loaded with a no delivery DNIC. With surface modification of this LQT peptide, the tumor stroma targeting LQT nanoparticle exhibits the most significant increase of tumor permeability due to downregulation of alpha SMA, which is a marker of activated PSC. So through further combination with chemotherapy drugs such as doxorubicin or gemcitabine, synergistic effects of anti-cancer drugs and anti-fibrotic and tumor vessel normalizing NO reflect on the most significant therapeutic effect featured by LQT DUX NO or LQT gem NO nanoparticles. So in addition to the oral and targeted delivery of NO, on-demand release of NO triggered by physical stimuli was also explored. In this study, a magnetic responsive NO release material, MagNOM, was developed through conjugation of NO delivery DNIC1-TG and MOF-derived iron oxide, followed by encapsulation in thermal-responsive PLGA microsphere. Upon pulsatile application of AMF to MagNOM, intermittent release of NO is well synchronized to the change of the surrounding temperature, which reveals AMF as an on-off switch for on-demand release of NO from MagNOM. Alternatively, after the burst release of NO upon 5-minute application of AMF, the AMF-treated MagNOM features a continued release of NO in a steady manner, which is similar to the slow NO release activity of MagNOM in the absence of AMF. This dual NO release phases of MagNOM controlled by AMF demonstrate its potential for the treatment of bacteria-infected cutaneous wound, which requires an antibacterial effect of high concentration of NO derived from MagNOM under AMF. Afterwards, subsequent degradation of AMF-treated MagNOM in the skin tissue results in the steady and local release of NO to accelerate the vessel regeneration, collagen formation, and wound healing. So in the last 5 minutes, I would like to briefly share that how the dinitrosyl ion unit as a single redox active unit can also utilize the metal ligand cooperation effect in pyroxylate dinucleate ion-10 DNICs to achieve the small molecule activation. So as opposed to the absent reactivity of pyroxylate dinucleate ion-9 DNIC towards CO2, its double reduced state DNIC 4 pyroxylate displays a metal ligand cooperative binding and activation of CO2, leading to the assembly of mononuclear iron-10 DNX3CO2, which is characterized by IR, single crystal X-ray diffraction, and other spectroscopic methods. Upon one electron oxidation of this DNX, formation of iron-9 DNX2Me occurs accompanied by the release of CO2. That is, as opposed to the dominant interaction between the 3-methyl pyrazole and the Lewis acid CO2 in this iron-10 DNX. One electron oxidation yielding a more acidic iron-9 core results in the enhanced iron-nitrogen bond and weakened nitrogen-carbon bond, which further triggers the release of CO2 and reassembly of DNX2Me. This competitive sigma bonding interaction between the 3-methyl pyrazole and the Lewis acid CO2 versus the redox active iron-2 unit further inspires our attempted study of reaction between iron-10 DNX3CO2 and redox inactive Lewis acid calcium triplet. During this reaction, dicationic calcium ion is proposed to bind to the carboxylate moiety and to induce the electron transfer from the iron-10 unit towards CO2, which is followed by the hydrolytic NC bond cleavage and dimerization of reduced CO2, leading to the formation of precipitated calcium oxalate and recovered iron-9 DNX2Me. So after recovery of DNX2Me, its subsequent reductive conversion into iron-10 DNX4 pyrazole facilitates the build-up of a synthetic cycle for capture and reduction of carbon dioxide into oxalate. Relying on the facile interconversion between the dinuclear and mononuclear DNX, metal ligand cooperation in dinuclear DNX4CO promotes the activation of dimethylamine boron, leading to the formation of a hydride bridging dinuclear DNX, which is evidenced by single crystal X-ray diffraction, IR, and proton and carbon-13 MNR. This isolated hydride bridging dinuclear DNX, moreover, is identified as the active intermediate for catalytic dehydrogenation of DMAB and generation of dihydrogen gas. Inspired by this metal ligand cooperation effect on catalysis, we are prompted to explore a robust cobalt and carbon material through an aerobic calcination of a cobalt-based MOF named ZIP67. Under a hydrolytic mechanism, catalytic hydrolysis of ammonia boron promoted by this cobalt and carbon material results in the efficient generation of dihydrogen gas. Based on the theoretical calculation and IR in combination with isotope labeling experiment, moreover, the identified cobalt hydride intermediate is assigned to the proposed cobalt-3 mu3 hydride and cobalt-4 mu4 hydride species, which can further convert CO2 into foaming. So in the near future, I hope that I can have the chance to share with you the translational application of this robust cobalt and carbon material as an anti-inflammation therapy against traumatic brain injury. So before I end my talk, I would like to acknowledge my collaborators for their help on a variety of perspectives. Also, the works I share today is supported by Ministry of Science and Technology in Taiwan, National Tsinghua University, Chang'an Memorial Hospital, and Majie Memorial Hospital. Finally, I'd like to express my great thanks to the diligent young talents in my lab. Thank you for your attention today, and I'm happy to take questions and suggestions.
Okay, anyone for Sean? Oh, yes, please.
Nice talk.
Thank you.
Jay. Yeah. So about your protein. So you use the DNIC to deliver into the cell. So what exactly that protein is? And the other question is, how can you know what kind of concentration is accumulated in the cell? And what is the releasing time of the, many questions, sorry.
Yeah, so no problem. That's all of these are very good questions. Can you still see my share screen? No?
I hope so. Slide share.
Okay.
Okay, so maybe I can answer the question directly. So the first one is that, okay, so what is a protein on the surface of the protein mediating the cellular uptake? That's the first question. So actually, that work is undergoing. We are also so desperate to understand this. So we are trying to utilize the proteomic approach to identify that what is the membrane protein, okay, for this cellular uptake of DNX. Okay, yeah, that's the answer to the first question. Okay, the second one is that, so at the moment, the way that we can categorize the concentration of DNX inside the cell is EPR. So I did not show the spin quantitation, the quantitative result today, but we are working on that. We can use the spin quantitation to determine the concentration of protein bound DNX, okay, inside the cell. Okay, and for the third one,
you mean the single cell level EPR? Single cell?
No. So the way that we do, actually, we use the student very different. So they use like 2 to 4 million of cells, okay, in order to get the EPR spectrum that you guys can see.
Okay, I see. Yeah.
Yeah. Okay, so that's for the second question. Okay, for the third one, okay, so we are trying two strategies. Okay, one is that because as we proposed, the binding of the DNX toward the DNX1 toward protein is the mechanism to initiate the release of NO. Okay, so one is that we can use the decay kinetics for the EPR signal to potentially reflect on the NO release kinetics inside the cell. Oh, that's the first thing. The second thing is that we are also trying to utilize the fluorescence probe. And then we are trying to monitor the fluorescence signal in a time-dependent manner. And we are trying to see whether these two kinetics are well correlated. And actually, we are trying to do the third way. We are trying to develop a responsive fluorescence active cell, okay, in order to monitor the intracellular delivery of NO. But that is still undergoing. Okay, so I hope that I answered all your questions.
Good, very good. Yeah, thank you.
Thank you.
Okay. Anyone? I also have a related question actually. So what I was thinking, if there is a free thiol available for the DNA to react and then transfer into the cells, then can you actually react with any of the small molecule that can possibly pre-react with the thiols and then see whether DNA can actually transfer into the cell? So if your hypothesis is correct, then and if the free thiol is responsible for the transfer, then and if you treatment basically protecting all the free thiols, then you may not see the transfer of the DNA into the cell, right?
Yeah, very good question. And actually, I see that also as a suggestion. Okay, so for that, we are working on two experiments. One is, as you mentioned, we are trying to do a pre-treatment of the cell with a thiol blocking reagent. And let's see if after the blocking, and then we don't see any cellular uptake of DNX, and then that means our hypothesis is correct. That's one way. Another way is that we are trying to utilize other kind of DNX precursor which can bind to the protein, generating a static protein bound DNX instead of the dynamic interconversion between the protein bound form and long molecular weight bound form. And if we can get that and then after treat that to the cell, and if we don't see the formation of intracellular DNX, and then I think that can be another way to demonstrate the thiol-mediated cellular uptake mechanism.
Right. Okay. Any other question? Otherwise, please thank him again.
Okay, thank you.
Okay, that's it for the first session of the first part of the afternoon session. We'll have a 15-minute break, so we'll be back at 5 to 4. All right.
So welcome to a new session, last session. We are going to start this session with Professor Christelle Hureau from Université Paul Sabatier in Toulouse, France. She took her PhD degree in Université Paris Sud in Orsay. I believe that's Paris-Saclay now. She took a habilitation degree later on in her current university, and that's called docent in other countries. That's something you do in many European countries to get a license kind of for teaching. So her talk today is titled Microcyclic-Based Ligand to Target copper-2 bound to the Alzheimer-related amyloid beta peptide. So, s'il vous plaît, Mademoiselle Hureau.
Can you hear me? Is that okay?
Yes,
Okay,
we can hear you.
Perfect. So thank you very much for the kind introduction, and I would like to warmly thank the organizing committee and especially Professor Lim for the very kind invitation. I'm really happy to be with you, and even if it's remotely, and to have the chance to share with you some of our last results. So today I will show you two different sides of what we are doing here in Toulouse, a more fundamental side, so linked to the importance of copper for reactive oxygen species production and also for the self-assembly of the amyloid beta peptide. And in the second part of my talk, as a consequence of this important role of copper in Alzheimer's disease, I will show you some of the copper targeting approaches that we have been developing for the last 10 years. So I would like to give you a brief overview of Alzheimer's disease first. So as you know, this is the most widespread neurodegenerative disorder, and there are two main reasons for that. The first one is that we are all getting older, and there is no curative therapy, meaning a way to stop or even prevent the disease. This disease is characterized by two hallmarks. The first one are intracellular tau tangle, which are made of hyperphosphorylated tau protein. And the second one are the senile plaques, which are extracellular and contain a high level of metal ions and of the amyloid beta peptide under a self-assembled form. And also, in the tissue, we can observe oxidative damages. So we are interested in Alzheimer's for itself, but also because this disease share many features with other amyloid-related diseases, such as, for instance, type 2 diabetes. So we are working based on the amyloid cascade hypothesis, which I show you here. So according to this hypothesis, the amyloid beta peptide in its monomeric and soluble form is inert for the brain, so not toxic for the brain, and found in healthy brains. But the more assembled form of this peptide under senile plaques or fibrils are found in disease patients, and we and others think that the process by which the monomeric peptides transform in the fibrillar peptides is important for the development of the pathology, and that during this auto-assembly process, there are some steps and some species which are toxic for the neurons. So this process is modulated by metal ions which are present in the synaptic cleft, mainly copper ion and zinc ion. And for copper, because it's a redox-active metal ion, there is also the production of an oxidative stress due to the formation of reactive oxygen species. So just a few words about this peptide. So it's 40 to 42 amino acid peptides made of two parts. One N-terminal domain, which is hydrophilic and which is a place where metal ions will bind, and a C-terminal domain, which is hydrophobic and involved in the self-assembly process. what you can see is that the metal binding site is very close to what we call the central hydrophobic core, so meaning that metal coordination to this site can impact the self-assembly process governed by the C-terminal part. So we and a lot of other groups in the world have tried to delineate the structure of the binding site of metal ion to this peptide from a structural point of view, and also the affinity of metal ions for A beta, because this parameter will translate the possibility of having the interaction between metal ions and A beta in vivo. And to make a very end, there is also some studies about kinetics of metal ion binding, and I give you here two very important papers about these topics. We and others have been interested in copper-1, copper-2, zinc, and the formation also of heterobimetallic complexes with this peptide. And here I show you a very short summary of what have been done in the last 10 to 15 years. And this is a very, very long story, but here all the groups are more or less agree on this coordination side. So for copper-2, the copper lies in a square planar environment bound by the N-terminal amine, the adjacent carbonyl function, two imidazole, one from histidine 6 and the other one from histidine 13 or 14. The copper-1 is bound in the linear fashion by two histidine. Here I drew histidine 13 and 14, but could be also 6 and 13 or 6 and 14. And zinc is tetrahedrally bound by two carboxylate and two histidine residue. And down I give you the affinity for metal ions. So what we can see is that copper and zinc have several binding sites, and they are in fast exchange. For instance, here you can have either histidine 13 and 14. I did not show you the data, but copper-2 and zinc-2 coordination are pH dependent. So here is a picture at physiological pH. The affinity value show us that the metal A beta interaction are physiologically relevant because it corresponds to the, it's compatible with the concentration of metal ion in the synaptic cleft. And from a pure coordination chemist, what was really interesting is that, as you can see, for a given ligand, for a given peptidic ligand, it is a metal site inside which imposes its binding site. So typically, square planar for copper-2 and tetrahedral for zinc-2. And this will have some implication for the reactive oxygen species formation and also for the impact of metal ions on A beta self-assembly. So first, I will give you a few words about ROS production, ROS formation. So ROS are obtained by the copper catalyzed reduction of the oxygen in complete reduction to superoxide, hydrogen peroxide, and hydroxyl radical. This reaction is fueled by the ascorbate reductant. And as the two binding sites of copper-2 of copper-1 are so different, we cannot imagine a direct electron transfer. So for that, what we propose is that we go through what we call an in-between state, which is shown here, and from which the reactive oxygen species production can occur. So starting from the copper in a geometry which is between that of copper-2 and that of copper-1, we can have this ROS formation. So first you reduce the copper-2 by ascorbate, and then the copper-1 form can react with dioxygen to form superoxide. And this state, this in-between state, is very low populated but accessible due to the high flexibility of the A beta peptide. And this in-between state has been determined by complementary indirect methods. And we do think that this in-between state theory can be extended to other peptide, intrinsically disordered peptide or intrinsically disordered peptide domain, protein domain, sorry. So now the second event of interest for the toxicity is the self-assembly of A beta peptide. So this process is typically a nucleation, elongation, polymerization process where you started from a mostly unfolded peptide and you finish with amyloids which are rich in beta sheets. And transiently, you form what we call nuclei, which are regarded currently as the most toxic species. To monitor this process, we monitor the content of beta sheet using a dye, which is a very well-known dye, so thioflavine T here, which acquired a very strong fluorescence upon intercalation into the beta sheets of amyloids. This S-shaped curve can be described mathematically by the function shown here, and there is two easy parameters to determine, which are the maximum of fluorescence intensity and then T1 half, which correspond to the time at which the self-assembly process reached half of the completion. So this is a very simple view of this process because in fact, it's autocatalytic and also heterogeneous. And it's extremely, the consequence, it's extremely difficult to get reproducible self-assembly process. But anyway, so this curve can be regarded as a fingerprint of the self-assembly process at play. And for copper and zinc, I've shown you here, some recent results we obtained, and what you can do, what you can see, that there is a metal-dependent effect. So copper or zinc doesn't impact the self-assembly process the same way. And this can be related to the fact that they occupy different binding sites into the peptide. You can also see that there is a strong metal-dependent metal-peptide ratio effect. And that for copper, we have a very low THT intensity in presence of one equivalent of copper. And this can be related to the formation of less ordered and thus probably more toxic assemblies. So that's why, in fact, we decided to target copper ions. We decided that copper is a therapeutic target of choice because it's involved in the formation of weakly structured A-beta self-assembly, and because it's redox active in the reactive oxygen species production, in contrast to zinc, which is redox inert. And so now I will show you several illustrations of the ligand we have designed in the last years to target copper. So ligand for copper 2, for copper 1, for either copper 1 or copper 2. I will spend a little time to tell you about the importance of zinc and that we must take it into account. And I will finish this part with kinetic aspect. So why also there is not only thermodynamics at play, but also kinetic issues. So to evaluate a copper ligand, we have a very simple test which rely on its ability to stop reactive oxygen species formation. And we monitor this process by looking at the consumption of ascorbate, because as you see, ascorbate fuels the reactive oxygen species formation. So if you look to the consumption of ascorbate, in fact, you look to the formation of reactive species. And we demonstrate that kinetically, that the consumption of ascorbate mirrors the formation of hydrogen peroxide, for instance. So basically what we do is that we have ascorbate and then we add either copper or copper A-beta, and so we consume ascorbate because we produce ROS. You can see that the production of ROS is less important in presence of A-beta, and this is directly linked to the very complex in-between state mechanism I've shown you before. So practically, to test the ligand, we have two different kinds of experiments. Either we incubate the copper A-beta and the ligand, and then we try to start the reactive oxygen species formation by adding ascorbate. And here in this situation, you see that the ligand was able to remove copper and to redox silence it because there is no ascorbate consumption. The other way of doing it is to do it during the ROS production. So you start by adding ascorbate, then copper A-beta, and at the end, you add your ligand. And if your ligand is able to remove copper from A beta, it will stop the ascorbate consumption. So this is what is schematized here. And so we started with a very simple silane derivative ligand, which has an appropriate copper-2 affinity higher than that of A beta. And we show that he was able to remove copper from A beta to form a copper redox inert complexes resistant to ascorbate reduction. So he was able to stop the reactive oxygen species formation. So this was a very simple ligand for a proof of principle, in fact. Then we move to more elaborated ligands, so such as this ligand, which is a pseudopeptidic ligand encompassing a phenanthrene moiety and an histidine moiety. And again, we were able to show that this ligand is appropriate to stop the reactive oxygen species formation. After, we also try to go to peptidic ligand, and we choose to study this peptide, so which is an N-terminally truncated form of A beta, which is physiologically reductant. And we were on this, inside this peptide, the copper-2 occupies a very well-known binding site called ATCUN for amino terminal copper binding motif, where it's bound by the N-terminal amine, the third is the histidine in third position, and the two amide in between. And with this purely peptidic ligand and physiologically relevant ligand, we were also able to show that this ligand can stop ROS production by copper A beta, full-length copper A beta. And last, more recently, we try with peptoid ligand, because if we want further to have more biomedical application, we need to have something which is resistant to degradation in the biological medium. So that was a kind of sort of example of what we've done targeting copper-2. But we have also shown that targeting copper-1, which is a strategy which is not strongly studied in the literature, is very appropriate. And for that, again, we try with a very simple ligand. And with this ligand, we were able to remove copper-1 from A beta and to form a copper-1 complexes, which is resistant to oxidation by dioxygen, and so which stop the reactive oxygen species formation. Last, what we can do is to target both copper redox state, because it's a very pragmatic approach. We don't really know what is the redox state of copper in the synaptic cleft, so we decided that we target both redox states. And in this case, we use an NTA-based ligand encompassing 3 histidine motifs. And this ligand is able to remove either copper-1 from A beta or copper-2 from A beta. And because it has a very, very slow redox process, it does produce ROS, but very slowly, so it decreases significantly the ROS produced by the system. So to make a brief summary, there is 3 kinds of possibility to stop ROS. Either you target copper-2 to form a copper-2 which is resistant to ascorbate reduction, or you target copper-1 to make a complex which is resistant to oxygen oxidation, or you target both redox state, but then you make a complex with a very slow redox ability. And then we wonder what happened in presence of zinc, because I told you in the introduction, zinc is also present, but it's present in very high amount compared to copper, meaning 2 orders of magnitude higher than copper. And so to target specifically copper, we need to have a very selective ligand that prefer copper over zinc. And to be extremely precise, it means that we should have a ligand for which the selectivity of copper versus zinc is higher to the selectivity of A beta. It means higher than 10 to the 4th, which is extremely difficult, in fact, to obtain chemically, because, for instance, the well-known EDTA ligand has a very low selectivity of 10 to the 2. So it's not so easy, so it's even quite tricky. And for that, we propose 2 different strategies. The first one relies on the use of a very rigid square planar ligand so strongly favoring the geometry preferred by copper-2 over zinc. So D4H for copper-2 versus tetrahedral for zinc. It's what we obtain with the silane type ligand, for instance. And there is another possibility is to use square planar ligand, but with amide containing function, because it will deprotonate and bind to copper-2, but not to zinc-2. And it's what we've done with peptide-like ligand. An open question is maybe the selectivity criteria, in fact, is easier to fulfill if you target copper-1 over zinc instead of copper-2. So that's something we are trying to answer currently. So of course, all the ligands that I've shown you before were able to work also in presence of zinc. It's true for the copper-1 ligand, for the copper-2 ligand, and for the copper-1, copper-2 ligand. And recently, we have even been able to obtain a ligand, a new one, so it's not shown here, that works even in presence of 250 equivalent of zinc compared to copper. So it's extremely selective for copper compared to zinc. And this is something which is required if you want to only target copper in the synaptic cleft. So now I want to give you a few words about kinetics. So until now, we discussed about thermodynamics, but I will try to show you that kinetics are also important. So I'll start with a very well-known ligand, so the cyclam ligand here. And if you incubate this ligand with copper A beta, then you form the copper-2 cyclam ligand, and this complex, and this complex is resistant to ascorbate reduction. So that's why there is no ascorbate consumption and no ROS production. But now, if you try to do the same thing during the ROS formation, during the redox cycling, you see here that you cannot stop the ascorbate consumption, so meaning that this ligand is inefficient when you start from a mixture of copper-1 and copper-2. And this is directly linked to the fact that there is a competition between the rate of copper-2 reduction by ascorbate and the rate of copper-2 capture by the ligand. To overcome this issue, we add a picolinato arm here to this ligand, and then it's the blue line here. You see that you can stop the ROS production during the redox cycling. And this is a pure kinetic effect. And we show that indeed the formation of the copper-2 complex using this modified ligand is much more faster than the formation of copper-2 complex using the parent cyclam complex. We were able to show that is also true for the cyclane family, and it's also true if you add 1 or 2 picolinato arms. And so it was a clear demonstration of the importance of the rate of copper-2 removal to have an efficient copper-2 ligand. More recently, we were also interested in cyclane and sulfur-containing cyclane derivative. So here again, it's a black curve here. Cyclane is not able to stop ROS production during the redox cycling. But if you exchange one amine by a sulfur atom here in green, then you recover this ability. And we explain that by 2 different possibilities. Either the substitution of an amine by the sulfur atom makes the copper-2 removal faster, or you can target copper-1, form the copper-1 species, which is fastly oxidized by copper-2. And once you have made the copper-2, then this copper-2 is redox inert. On the same figure, you can also see that we try with a ligand where we substitute 3 amine by 3 sulfur atom. It's a purple curve here. And you see that the ROS production is lessened but not completely stopped. And in fact, we designed this ligand to target copper-1. And what we think is that copper-1 is removed by this ligand, but can be oxidized to copper-2, even if it's very slow. But once the copper-2 is formed, then it goes back to copper-2 A beta, because A beta is stronger in binding copper-2 than this ligand. And again, so we show that taking into account kinetic issue is very important for the design of a copper-2 chelator. So to briefly summarize, we show that we should have a ligand that is able to remove copper from A beta so that its affinity should be higher than that of A beta peptide. And the complex form should be redox inert, not to produce ROS on its own. The ligand should work in presence of high amount of zinc, and this is a very difficult criteria to fulfill. And last, but I would say not least, it should be fast in binding copper because there is a competition between copper removal and copper reduction. Now, in the last 5 minutes, I want to give you a very short overview of what we've done recently with a POM ligand, which has very interesting additional properties. So why we choose POM? So POM is for polyoxometallate, because there was a very inspiring literature which shows that POM are able to penetrate the blood-brain barrier, which is of course very important if you target Alzheimer's disease. And it was also shown that POM can modulate A beta self-assembly. From a pure chemist point of view, we are also interested to go from molecular ligand to supramolecular ligand. And POM are very suitable because they are water soluble and they show great structural diversity. So the result I will show you have been obtained with this Kegin POM, which has a lacuna here, so a hole that is able to welcome a D cation, for instance. So first, we try to see if this ligand, this supramolecular ligand, is able to remove copper from A beta and stop ROS production, and the answer is yes. It can prevent the ROS production or it can stop ROS production during the ascorbate consumption. And this was a property that has never been shown before. Next, we look to the properties of POM to modulate the A beta self-assembly. So here you have the APO A beta assembly and the assembly in presence of one equivalent of Kegin POM. So the most striking difference is that you have a more intense THT fluorescence here that mirror an increase, either an increase in the quantity of fibrils you form or a different morphology with more order fibrils formed in presence of POM. So to check that with stem picture, in fact, it's probably both because we can see that there are more fibrils, and we can also see that the morphology of the fibrils is the difference between APO A beta and A beta in presence of POM. And this effect is very likely due to electrostatic interaction between the anionic POM and the positively charged residue of the A beta peptide. Then we had a look on what happened in presence of copper. So as before, copper A beta modified the self-assembly of A beta. It's a blue line here, and when you add POM, then you have a new curve, the purple one, and this curves correspond to this chemical equation where the Kegin, the lacunary Kegin, has removed copper from A beta. So in the mixture we have APO A beta and the copper substituted Kegin. And what we can see is that then in this case you have a different assembly than with A beta alone. And this is a very important feature because with molecular ligand, what you obtain is when you add your ligand starting from the copper to A beta curve, then you go back to the A beta alone curve. So with molecular ligand, you go back to a similar assembly than the one of APO A beta. So briefly, we have been able to show that the POM itself and the complex formed in presence of copper, they do modulate the self-assembly of A beta. The fluorescence intensity is higher, so it's probably mirrors the formation of more order, which probably means less toxic assemblies. So now to conclude, I hope that I convince you that metal ions are really important and are the crossroad of several processes involved in Alzheimer's disease. And we focus on copper as a therapeutic target, but the zinc can also be considered as a therapeutic target. And so in the team, we are also very focused on trying to have a dual strategy. So fundamental studies of the mechanism of ROS formation or of E-beta self-assembly in link to therapeutic approaches. And recently, we and others have defined the required properties a drug candidate should have. I strongly believe that it's really important if we want to really inspire the design of new and efficient drug candidates against Alzheimer's disease. And I think it's time for me to thank all my collaborators. So mainly Raphael Trippier and Oraculac for the macrocyclic ligand, and all the other collaborators for the other kind of ligand, the technical staff from my lab, and all the students, past and present, of the Alzheimer, amyloids, and bioinorganic chemistry team in Toulouse, the funding agency, of course, essential, and my institutional administration. And I thank you very much for your kind attention.
Yes, thank you very much for the nice talk. We have a question online, actually, so let's start with that.
Okay.
Professor Yun-Ming Wang? Professor Yun-Ming Wang, you can hear me? No? Okay. Maybe we can come back to him later. Do anybody else have a question in this forum? Then maybe I can start with a simple question. You are talking about copper and zinc here. So do you have any plans to go on to other metals here? Like, I mean, your ligands, are they actually workable on other metals as well?
So it's quite well known that the three main metal ions linked to Alzheimer's disease are copper, zinc, and iron. And but iron is not really accessible because it's under the form of nanoparticles. So we try to see the coordination of iron to E-beta, and it's not really strong. So we really focus on the interference with zinc and not with iron for these two reasons, because iron is not really accessible, and the ligand are, and if we try the selectivity against iron, the ligand are also efficient.
Okay. All right. Okay. We have a question from Professor Lin.
Hi, Christine. Nice talk.
Hi, Mi.
Hello. I have a question since, because you know very well the copper can bind, the second copper can bind also, right?
Yeah.
So depending on the stoichiometry, the metal to the
Yeah.
A-beta. So what do you think about the in-between state, you know? It's sorry, I was curious when I'm reading your paper.
That's a good point. So clearly, so we decided, for matter of simplicity probably, that only the first copper is really relevant. Mm-hmm. The second site is, if I remember well, 3 orders of magnitude less strong than the first one. That doesn't mean that it cannot be populated. I fully agree with you. And we can see that, for instance, in the assembly process. So there is a difference between 1 or 2 equivalent of copper per peptide. And for the ROS, we didn't try, but that's really a good point, because probably the second copper which will be more loosely bound to the peptide, will be more efficient in producing ROS, sorry, and with a more classical ROS production mechanism.
I see.
You're
I
right.
see. Okay. Thanks. Nice talk.
Thank you.
Okay, thank you. So we are actually right on time, so let's try to keep that. Thank you very much, Professor Hureau.
Thank you.
Next talk is from Professor Chen Yu from Hureau University. She got her PhD from National Taiwan University and went on to do postdocs in Academia Sinica. And she got assistant professorship in National Central University in Taiwan until 2 years ago when she got the professorship at Hubei University. Her talk today is titled Structural Basis of Temperature Effect and Coenzyme Bispecificity of Ketol Acid Reductor Isomerase. Professor Chan? Please, go on. Oh, excuse me, problem with the sound apparently.
Okay.
Oh, now we hear you. Good.
Okay. Good afternoon, ladies and gentlemen. Thank you, Professor Lee, for your kind introduction. I'm very honored to have this opportunity today to share our research work by using advanced cryo technology.
Professor, we cannot see your PowerPoint. Could you share it again? Could you share your screen?
Okay. Yeah, I share my screen already.
Once more, please.
Once more,
Yeah.
okay. Can you see my screen?
Yes, thank you. Hold on
Okay,
a second. It's okay?
Okay. I continue. Okay.
No.
Okay.
Could you turn off your sharing and then share it again?
Okay.
Yeah.
Okay, something wrong with my. Okay. Wait for me.
Now it looks like we can turn. Oh, no.
I will find two files.
Could you try it again? Turn off screen sharing and then turn it on?
Yeah. I tried. Okay. Please wait for me. I don't know what happened. Can I connect into room again? Because I can.
Can you do the screen share? Because when you look at in here, your slide is not on the screen share. So could you try one more time? Screen share and.
Yeah, I sure again.
Yep. All right.
We see.
Now it's okay.
We only see part of your screen, not the whole screen.
Why?
We only see the kind of
Only partial.
Yeah.
of your slide. So.
Upper left corner we see.
I need to share the full screen, right?
Yeah, full screen.
Yes, yes.
Oh, but I don't know how to.
On the right side. Okay.
Where is the full screen item? Oh,
Okay, just hold on there. Our technical team will change it. We'll do our best. So.
because I cannot find the item for the full screen.
Wait a second, and just turn on your slide, and we'll try to change your slide up here. So.
Oh.
All right.
Okay,
So,
perfect. Yes.
Everything is okay. So now we can start.
Right. We didn't have to go to commercial.
It's okay?
Yeah, everything is okay.
Yeah.
Okay.
Please go ahead.
Okay. I continue, right? Can
Yes. Yes, please go ahead.
Okay. In 2017, Prof wins the Nobel Prize in Chemistry. Three pioneers of Prof technique, Jackie Bush, Joaquin Frank, and Richard Henderson, share the prize for their contribution to the development of Prof. Now the Prof technique can image biomolecules in solution at a near atomic resolution or even at atomic resolution. In fact, this method has moved biochemistry into a new era. Prof was once termed globalology because of its low resolution image. Now Prof can produce atomic resolution structure rapidly from virus particle to the enzyme complex. No longer globalology. Now Prof is getting into molecular details. The molecular details that are essential for the better understanding of proteins' function chemically and also critical for drug discovery. Before 2013, Prof typically provide a resolution of about 10 to 20 mtron, which might reveal the overall shape of a protein, but has no molecular details. However, in the past few years, advances in technology have led a dramatic increase in the number of Prof structures, increasing in the number of Prof structures, achieving resolution at about 3 mtron or better. Keto acid reductase isomerase carry is the second enzyme in the biosynthetic pathway of BCAA, which are essential amino acids for humans and include valine, leucine, isoleucine. There is a considered market for these amino acids produced in microorganisms for use in animal feed and dietary supplement in dietary supplements for humans. Carries the bifunctional enzyme which catalyze the unusual two-step reaction. The first step is magnesium-specific archaeal migration. Transfer the methyl or acyl group from C2 carbon to C3 carbon. The second step is NADH or NADPH dependent reduction. The cofactor transfer the hydride to reduce the 2-keto group to hydroxy group. Recently, Carrie also attracted much interest in biofilm production. Francis Arnold is a 2018 Nobel Prize laureate in chemistry. Arnold's group has engineered the BCA pathway in E. coli to produce isobutanol from glucose. In this pathway, two enzymes, carry and alkyl dehydrogenase, require to use the nicotine amide cofactors. However, only NADH molecule can be produced from glycolysis. If these two enzymes prefer to use NADPH, then this pathway has a cofactor imbalance problem. Therefore, NADH preferring enzymes are required in this biosynthetic pathway. Arnold's group has reversed the cofactor preference of carry and use NADH-dependent ADH in this modified pathway to increase the yield of isobutanol successfully. Most carry has a strong preference for NADPH over NADH. Structurally, NADPH and NADH are different only in a phosphate group at the 2' position of the ribose. However, most enzymes can distinguish these two cofactors specifically. NADH is much cheaper, more stable, and more easily recyclable than NADPH. So the NADH preferring enzymes are desirable for industrial application. In our study, we identified a SSO carry from the hyperthermophilic Archaea, Sophaloba solfatarix. The Sophaloba species grows best at high temperatures and low pH. Therefore, proteins from Sophaloba are of interest in biotechnology and industrial applications because of their thermal stable property. Recombinant SSO carry protein was overexpressed in E. coli and purified to show high purity on SDS page. The gel filtration results show that the major population of SSO carry in solution is a dodecamer with molecular weight of 440 kilodalton, making it suitable for column structure determination. Based on CD analysis, this enzyme is heat stable and acid tolerant. The kinetics data show that SSO carry can use either NADH or NADPH as a cofactor. The Km and the Kcat value of these two cofactors are almost identical, indicating that the cofactor preference of this enzyme is bispecific. The SSO carry is a thermostable enzyme. Its activity increased with elevated temperature from 40 to 80 degrees Celsius. However, this enzyme lost most its activity at a pH value greater than 7.8. The carry monomer is composed of N domain and the C domain. N domain is a Rossmann fold for binding coenzymes, and the C domain is a knotted structure where two monomers intertwine tightly through alpha helix to form a dimer. The dodecamer is assembly by six dimers, which are placed on the edge of the tetrahedron to form a tetrahedral geometry. To study the cofactor preference structurally, we solve the column structure of SSO carry in complex with NADH or NADPH at a resolution of about 3.4 angstrom. The electron density map of NADH is resolved clear, and the NADH model fit into column map very well. It is interesting to understand how carry enzymes specifically distinguish between these two cofactors. The side chain of asparagine 45 in the cofactor binding loop can undergo a conformational change and make different contacts with these two cofactors. In NADH complex color in yellow, N45 forms two hydrogen bond with the 2' hydroxy group of the ribose. In the NADPH complex color in gray, N45 can move away to accommodate the additional 2' phosphate of the NADPH and make another hydrogen bond contact. This result was published in the JACS and featured on the JACS cover in April 2019. I designed this cover image and work with my former graduate student, Dr. Lin Guanfu and Xie Dongling at the National Central University. In 2019, Hubei University purchased a set of the newest cryo machines and need cryo experts and users to join their research platform. That gave me a job opportunity. In the beginning, I extended my cryo study on carries at Hubei University in October 2020. 7 thermophilic and dual coenzyme utilizing carries from archaea and bacteria has been identified. The kinetic data show that 7 thermophilic carry were highly active at 50 degrees Celsius, all with dual coenzyme specificity and varying in preference, varying in preference. We solve cryo structure of these carries in complex with NADH or NADPH to reveal how these carry protein interact with their coenzymes. The resolution of all cryo structure is between 2 to 3 mtron. The best one is 1.98 mtron. For these thermophilic carries, it is worth to mention that magnesium coordinating water at the active site of carry are clearly visible in the cryo maps. That is a feature generally observed in the high-resolution crystal structure. We have never seen this before in the SSO carry structure. The upper panel, the structure was determined in Academic Yasunika, Taiwan. We cannot see the magnesium coordinating water in this structure. In the literature, only 2 cryo structures, beta-glycosidase inhibitor complex and the RNA structure of E. coli 50S subunit at 2.2 mtron resolution show the similar magnesium coordinating waters. The most exciting things that happened recently is that we broke the resolution barrier of 2 mtron. We got the first 3D cryo map sharper than the 2 mtron with Titan Quills, TM, and the KAST camera. Here we highlight the high resolution features such as holes in the aromatic rings of tyrosine phenylalanine and the tryptophan residue, a feature typically observed in the crystal structures at a resolution greater than the 2 mtron. The well-ordered waters column magenta and features of the zigzag structure of extended side chains such as glutamine asparagine, arginine, and so on, are also visible clearly in the electron density maps. In this study, we found 3 patterns to describe how this enzyme can use the same binding package to adapt to different coenzymes. In NADH complex structure, 1 sulfate in IA carry and 1 phosphate in SEC carry anchored in the loop was observed. For IA carry and SEC carry, their CAM value toward NADH in phosphate buffer were reduced, while the KCAT increased respectively compared with those in sodium chloride. Therefore, their catalytical efficiency in phosphate buffer is higher than those in sodium chloride. This kinetic data and the structural observation suggesting that phosphate and sulfate can facilitate NADH binding to IA carry and the SEC carry by mimicking the two prime phosphate of NADPH, thus enhancing the enzyme activity. The second, in NADH preferring carries negatively charged residue like aspartate in TP carry, and glutamate in SL carry, often serve to repair the two prime phosphate of NADPH, like here, and accepted hydrogen bond from the 2' 3' diol of the ribose in NADH. The third pattern is as observed in HS and MR carry. Along with the conformational rearrangement in beta-2 alpha B loop, polar but uncharged residues such as serine, and or asparagine often serve to mediate the interaction with the 2' phosphate or 2' hydroxy group upon different coenzyme binding. In summary, some breakthrough of cryo-EM technique we have done at Hubei University recently. We observe the magnesium coordinating water clearly at the active site of the thermophilic carry and obtain the high resolution quantum structure of carry complex greater than 2 mtron. We also found the 3 patterns to uncover the molecular basis of coenzyme switch for the thermophilic carries. According to previous study, comparison of crystal structure between different carry complexes show that domain movement occurs when the ligand binds to protein. However, SSO carry lack this induced fit mechanism when the cryo-EM structure were determined at 4 degrees Celsius. In general, cryo-EM samples are prepared at 4 degrees Celsius. However, many enzymes have a low activity at this low temperature. In our previous study, SSO carry has no enzyme activity between 4 to 36 degrees. Therefore, we propose that SSO carry has no conformational change upon ligand binding because the enzyme does not work at this low temperature. We decided to solve the cryo-EM structure of SSO carry at high temperatures to see what happens when this enzyme is active. We heat the protein sample in the water base and then vitrify the sample at high temperature by vitrable machine. Consequently, the cryo-EM can capture the high temperature protein structure by rapidly freezing the sample into the amorphous ice. We saw 12 cryo-EM structure of SSO carry in magnesium complex or ternary complex at least 6 different temperatures with the resolution of 2 to 3 mtron. Compared to the cryo-EM structure between different states, show the temperature increase or ligand binding can cause the end domain movement toward active site with different rotational angles. In this video, I moved 6 structures from 4 to 70 degrees together to show the protein conformational change induced by the temperature. Left in magnesium complex, increasing temperature result in the end domain closure with the rotational angle of about 4 degrees. However, in the ternary complex, increasing temperature causes a larger end domain movement with the rotational angle of about 13 degrees. The ternary complex structure displays the larger end domain closure than that in the magnesium complex. Here we show ligand-induced fit of SSO carry by video. At 4 degrees, no ligand-induced fit observed because the enzyme has no activity at this temperature. At 70 degree is physiological temperature of SSO carry. Ligand binding causes the end domain closure significantly, and the rotational angle is about 10 degrees. Structural analysis indicates that the totally inactive magnesium complex at 4 degrees Celsius can reach the most actively ternary complex at 40 degrees in two alternative pathways. Heating first, followed by ligand binding at 40 degrees, contributing about 4 degrees and 10 degrees of end domain closure, respectively. Over the second pathway is ligand binding first at 4 degrees Celsius without conformational change, followed by heating to 70 degrees Celsius to achieve full end domain closure. Comparison of magnesium complex at 4 degrees Celsius with the ternary complex at 70 degrees Celsius. The total end domain closure is about 15 degrees, which is in good agreement with the sum of the two steps from either pathway. Consequently, induced fit mechanism of SSO carry can be dissected into ligand-induced and temperature-induced effect. We found that the temperature-induced conformational change of a ternary complex is a stepwise process. First, at the reaction center, CBD reorientation occurs during 4 to 36 degrees Celsius. Second, the coenzyme NADH shifts the position during the 36 to 55 degrees Celsius. Finally, the end domain moves towards active site during 55 to 70 degrees Celsius. Here we show the temperature-induced conformational change of the ternary complex by video. This is a 3D cryo map for the dodecamer. Turn it into protein structure, showing temperature effect on the dodecamer. Looking into the dimer, showing the temperature effect on the dimer. Looking into the molecule details, first, CPD reorientation. Then the coenzyme NADH shift position. Finally, the entire end domain moves toward active site. This result was also published in JACS in December 2019. This paper was selected as JACS Spotlight article and recommended by faculty opinion. Due to the time limitation, I skip several slides and go to the summary. For the SSO carry, temperature-induced conformational change of the SSO carry ternary complex start at the reaction center, extend outward to the coenzymes, then the entire subdomain closure. In this feed mechanism of SSO carry can be dissected into the temperature-induced and the ligand-induced effect. The most important thing is that protein structure need to be determined at its physiological temperature to show the real active form. Here, I would like to thank the Korean machine time supported by Dr. Tsai-Te Lu and the Taiwan Protein Project. I also thank my former graduate student at the National Central University, Dr. Lin Guanfu, Xie Dongling, and Tsai Mengru. And my current master student at Hubei University, Wu Pengchen, Yuan Jue, and Ma Ying. In addition, I truly appreciate all support from the Dr. Ke Ziping, Dr. Zhang Yuanzhi, Dr. Lin Bolin at Academia Sinica, and Dr. Huang Junxiang at NSRC. We work together to finish a lot of beautiful research work. This is the end of my presentation. Thank you for your attention. I hope you all enjoy my talk about ProEM. Thank you.
Thank you very much for this talk. We now have time for questions.
No question in the YouTube.
I cannot see any. So
Hi, Dr. Chen. This is SJ. Thanks for this wonderful result, and thanks for joining with us. Actually, my question is you said that the conformational change from the ligand and also conformational change because of the temperature, it could be two-way. Yeah. So this is a protein of somophilic protein. So how do you think about that? The conformational change by the ligand is more important aspect, or conformational change by the temperature is more the directly influence for the conformation of the protein. How do you think about that? Yeah.
Yeah. The slide I do not show is about the temperature effect and the ligand binding on the mesophysical enzyme. Based on these two enzymes, thermophilic and mesophilic carry. I think from the structural data, I think the ligand binding can cause significant conformational change than the temperature effect. The temperature effect is minor, but I think it's also play an important role. I can show. Yeah.
I understand. Based on your answer, so my thinking is that the conformational change by the temperature might be lower the binding affinity. It could lower the binding affinity to the NADH or NADPH. Is it true? Possible?
Oh, yes. At a low temperature, the binding affinity of the ligand is lower than the high temperature. Yeah, it's true.
Okay, thank you. And if there is no question, one last question, because of the last question is that you show the binding affinity to the protein to the NADH is not the binding affinity. The Km value is around the millimolar value. So what is the usual Km value between the NADH and the protein? Because I think it will be so strong. So it's as a cofactor binding affinity between the NADH to the protein. So.
Pardon? I don't get the problem.
Yeah, I'm asking you the question about what will be the binding affinity between the NADH to the protein as a cofactor.
It's around in the micromolar range. Micromolar range.
Okay, thank you.
Are there any other questions here? If not, let's thank Professor Chen for a nice talk. So now it's time for me to take a nap. So I'll present the next next chair here, Professor Lee.
Right. Finally, we are at the last step of the symposium. And the last speaker of the symposium is Professor Youngmin You from Ewha Women's University. And he obtained his PhD at Seoul National University in 2007. And he started his independent career at Kyung University in 2013. And then he moved to Ewha. And now he's going to present what he has been done during his career at the Ewha Women's University. Please welcome Professor Youngmin You.
Thank you for the introductions. I'm very excited to talk about excited state process. We have seen in this symposium a variety of biological and biometric redox chemistries. Nature is so smart to utilize these transition matters. This transition matter, as you see here, this transition matter serves as an active center for very highly thermodynamically challenging reactions, which are difficult to mimic. I believe that the one way to accomplish the mimicking this thermodynamically challenging reaction is to use photons. Upon photoexcitation, this is an electronic configuration of photoexcited state. As you see here, upon photon absorption promote electronic transition from HOMO to LUMO. Now you can see that these singly occupied molecular orbitals are generated. This single occupancy enables electron transfer with a driving force greater than that of the ground state. My group has been involved in the development of photoredox and photochemical reactions. Particularly, we are interested in the elucidating the mechanism underlying the photophysical processes. To me, being a member of Korean Bioinorganic chemistry is good because we have very excellent collaborators here who are doing very interesting redox reactions. I have to say that I'm always inspired by the enthusiasm of you, but I have to say that my previous photoredox catalyst systems suffer from intrinsic drawback. This is a electronic configuration of an excited state. As you see here, photon absorption promote electronic transition from HOMO to LUMO. Now there is a lower single occupied molecular orbital and higher single occupied molecular orbitals. And this electron transition is done by absorption of photon, which the energy is in resonance with band gap energy of molecules. So this singly excited state can perform the one electron transfer to form this electron transfer state, and the redox power of the electron transfer is shown here. You can see that we can increase the redox power for electron transfer when we increase the band gap energy of catalyst. But unfortunately, we cannot increase the band gap energy as much as we want, because the use of photon sources, including the solar radiation, provide us a visible energy photons. And the UV photons are destructive for the redox transformations. So there is always a trade-off between a redox power and photon utilization, and we have to overcome this trade-off problems. The nature is so smart to solve this problem. Shown here is light harvest systems of some biological system. You see then there are an array of chlorophylls. You can see that these chlorophyll arrays are found in photosystem 1 and photosystem 2, and each of the light harvest center is independently excited by photon absorption. These two independent photon absorption builds up the large large electrochemical potentials for electrochemical conversion, which are thermodynamically very, very challenging. So my research is to mimic the biological multiphotonic redox catalyst systems. So I'll be talking about 3 recent approaches. One approach is based on the doublet photocatalysis. As you see here, this doublet species can absorb second photons or photons to form this very unstable excited state. You can see that now the electron is now at the non-frontier molecular orbital, which are highly reducing. So this can allow us to overcome the band gap limitation problems. The second approach is based on triplet fusion. As you see here, 2 triplet state, they can combine together to generate a singlet excited state and ground state. This single excited state energy is greater than the originally generated formed photoexcited state, so we can also overcome the band gap limitation of photocatalyst. The third approach is actually a reversal of triple fusion. Under certain conditions, a single excited state can dissociate into 2 triple states. This single fission generates 2 triple states, which facilitate 2 electron transfer. So overall, this is a 1 photo-induced 2 electron transfer catalyst. So we can obtain quantum yield greater than 100%. Right. Let's begin with the first approach. Shown here is shown here is a cycle of doublet photocatalyst. PC here is a catalyst. This photocatalyst can absorb the first photon and now is become a neutral excited state. And this neutral excited state can be reductively quenched by sacrificial electron donor into to form a radical anion. This radical anion is short-lived. However, it can absorb second photon to be promoted to excited state. As you see here, this final electron is now at the higher line molecular orbitals, which is highly reducing. So we can obtain very large redox power from this excited state radical anion. This is good, and this appears to mimic the natural photosynthetic systems. However, you can see that this radical anion, the excited radical anion, they have this identical doublet spin state. So this excited state is very short-lived. Its lifetime is as short as several picoseconds. So this mechanism is debated by several groups that it is too short-lived, so it cannot steer the diffusion-limited redox reactions. So I decided to investigate the mechanism of the doublet photoredox catalysis systems. Right. So to facilitate, to enable our study, we choose these organic molecules as a catalyst. I'm sorry not having the metals here, but these organic molecules displays a very long excited state lifetime, even without the transition metals. You can see that there is an equilibrium between singlet excited state and triple excited state due to the small electron exchange integral between HOMO and LUMO. This excited state equilibrium permit excited lifetime as long as several microseconds. So this one can perform redox catalysis even without the help of transition metal, which provides spin-off coupling effect. Okay. So what we first did is to examine this catalyst for organic transformation. We found that this catalyst can catalyze bordylation of aryl bromide. We also found that this catalytic bordylation requires photons and catalysts and DBU sacrificial electron donors. We also find that the addition of radical trap or electron trap abolish the reactivity, which indicate that this catalysis involves electron transfer step as a key process. Actually, the Born-relation reaction requires 2 photons. We found that, as you see here, there is a quadratic dependence between the product mole and photomoles, which indicate that 2 photons are involved in this Born-relation reaction. We also determined the quantum yield for the Born-relation reaction. The black bar is quantum yield calculated with assumption that the single photon is involved in the catalytic transformation. You see that the quantum yield is very large, even larger than theoretical limit for 1 photon process. So this is impossible because the Born-relation reaction does not involve radical propagation steps. The red bar here is a quantum yield, which was calculated with 2 photon process. Now the quantum yield is reasonable because it's lower than theoretical limit of 50%. The overall, all this data indicate that the Born-relation reaction is steered by 2 photon absorptions. This claim is supported by our electrochemical measurement. So we actually determined the redox potential of the excited state and redox potential of radical anion. This potential, actually oxidation potential of radical one electron reduced catalyst is minus 1.49 volt versus SC. This potential is less negative than the reduction potential of a 2 substrate. So electron transfer from this 1 electron reduced catalyst to the substrate is not feasible. Electron transfer from neutral excited state to this substrate is also impossible because this excited state oxidation potential of this catalyst is less negative than reduction potential of the substrate. So these comparisons suggest that one photon generated species such as this excited state and radical anion are incapable of performing redox Born-relation reactions. So we turned our attention to second photon absorption. This red spectrum is UV visible and IR spectrum of radical anion of this catalyst. You see that there is large spectral overlap between this red spectrum and white LED emissions. In sharp contrast, the black spectrum is absorption spectrum with neutral catalyst, and this black spectrum shows very negligible overlap with white LED spectrum. So we found that this radical anion can absorb the photons from white LED, which we provided. The band gap energy of radical anion is about 1 electron volt, so we can calculate excited state oxidation potential of radical anion, which is minus 2.25 volt versus acid, which is very negative. So electron transfer from here to the aryl bromide is now thermodynamically allowed. So all the data indicate that the radical anion, specifically excited state radical anion, may be the key catalytic intermediate in the Born-relation reactions. So these our circumstantial evidence indicate that 2 photons are involved. However, energy transfer and charge transfer complex formation are not involved in the activation of catalyst because energy transfer is from this excited catalyst to substrate is not possible because there's no spectral overlap between the fluorescence spectrum of catalyst and the absorption spectrum of this substrate. And you can see that there's also no new absorption band when you mix DBU and the catalyst upon photo irradiation, which indicate that charge transfer interaction does not occur here. Right. So we decide to monitor each step toward activation of a catalyst. The first step of the activation of catalyst activation is the formation of radical anion. This step is done by photoinduced electron transfer from DBU to the excited state catalyst. This activation step is actually competes with the intrinsic fluorescence pathways of this excited state catalyst, so we can employ fluorescence technique to monitor this electron transfer process. As you see here, the fluorescence spectrum of the catalyst, and fluorescence lifetime of the catalyst decrease upon increasing the concentration of the DBU, and this indicate that the DBU interact with the excited state catalyst to form non-emissive species. We were able to determine the bimolecular quenching rate constant, which is 10 to 7 per mole per second. Okay, once the radical anion is generated by electron transfer from DBU, and this radical anion actually disappears rapidly. This disappearance is due to charge recombination between these germinated radical pairs. We employed nanosecond transient absorption spectroscopy to follow this charge recombination step. This red reason is absorption spectrum of radical anion catalyst, which is generated by electron transfer from DBU to excited state catalyst. We are able to monitor the decay of the radical anion signals by second order kinetics analysis. We are able to determine the bimolecular rate constant for charge recombination. It is found that the charge recombination is ultra fast. A rate constant is as large as 10 to the 8th per mole per second. So this is unhappy. However, this excited radical anion can still promote electron transfer to the bromide, aryl bromide substrate. This electron transfer generates radical anion of this substrate, sorry about this typo, and neutral catalyst. Actually, we performed the steady state spectroscopy measurement for the radical anion. As this one is spectral electrochemical cells under dark, under photo irradiation in the presence of this aryl bromide substrate. You see that this radical anion absorption band decreases when you shine the light and when we add it aryl bromide substrate. However, under dark, this characteristic absorption band of radical anion is weakly affected. So this data indicate that there is electron transfer from the excited radical anion to this aryl bromide. We followed the kinetics. We determined the kinetics of the electron transfer step using a femtosecond transient absorption spectroscopy. And the data is shown here, but it's too noisy to make long story short. We were successful in determining electron transfer rate. Its electron transfer rate is actually very, very fast. I'll show you this mechanism next slide here. Shown here is the overall mechanism of bodylation of the aryl bromide. These red arrows are activation steps of the catalyst, and blue arrows are deactivation steps. What we find from our mechanistic study is that the most destructive deactivation step is this one. The excited radical anion is very short-lived. Its lifetime, it decays at a rate of 10 to 10th per second. It's rapidly disappears. And this rate is actually greater than diffusion rate. So we believe that radical anion catalyst and this aryl bromide substrate form a complex before the second photon absorption. And this mechanistic finding is the first one. So we are happy to see this kinetic data. Right, let's move on to second topic. This is triple fusion photocatalyst. Triple fusion catalyst requires two species. One is a sensitizer, the other one is an annihilator. The sensitizer absorbs photon to form triple excited state. Then triple energy transfer happens to populate the triple state of an annihilator. This triple excited state annihilator is long-lived, so they eventually collide together to form, to generate singlet excited state and ground state. I want to emphasize here that this newly generated singlet excited state is higher in energy than the originally populated singlet excited state. So overall, this process is a photon upconversion. You can shine the low energy light and generate high energy photons. So we decide to employ this triple fusion system for redox, not redox, the photocatalytic system. We employed platinum octaethyl porphyrin as a sensitizer and diphenyl anthracene as an annihilator. This triple fusion system can generate an upconverted blue fluorescence emission with a peak wavelength of 418 nanometer. And this blue emission can photoactivate FAD in fatty acid photodecarboxylase. And this photodecarboxylase enzyme can oxidize alkanoate into alkanoate radicals to cleave this C bond to form alkane as a products. So to examine this idea, Dayun prepared polystyrene nanoparticles doped with platinum octaethyl porphyrin sensitizer and diphenyl anthracene annihilators. You see, this polystyrene nanoparticle doped with sensitizer and annihilators are highly spherical with a diameter is about 300 nanometers. They are quite stable. So then photoexcite the nanoparticle, triple fusion nanoparticle system with green LED with a peak wavelength of 550 nanometers. This green LED photoexcitation generate anti-Stokes-shifted blue emission with a peak wavelength of 418 nanometers. And this fluorescence emission is from this diphenyl anthracene. Then carefully quantified the upconverted blue fluorescence emissions with varying the excitation power. As you see here, there is a change in slope here from roughly 2 to 1. This 2 to 1 slope change indicate an occurrence of triple fusions. And threshold power is very, very small, so we are happy with this small threshold power for triple fusion. Then Dayun examined whether this triple fusion nanoparticle can photoactivate fatty acid photodecarboxylase enzyme. And what she did is fluorescence titration experiment. This is a upconverted fluorescence spectrum of these nanoparticles, and this spectrum was obtained with increasing the concentration is photoenzymes. You see the decrease in upconverted fluorescence emission, which indicate the energy transfer from the nanoparticles to the photoenzyme. Our initial attempt to fit this titration data to Stonborn plot was unsuccessful, but Dayun was clever to use letters modification of Stonborn equation. The letters equation gives the successful fit of data point to theoretical equation. The energy transfer rate is very rapid with rate constant about 10 to 9 per mole per second is it can rapidly photoactivate the photoenzyme. Right. Then Professor Jin Byung-bak at Ewha, his lab examined the photocatalytic ability of our triple fusion system. What his lab did is to incubate the cells with the nanoparticle. Then the whole cell experiment demonstrate that under green light irradiations, the fatty acid for the enzyme expressed in the whole cells can convert the fatty acid to this alkane. So we are happy with this result, to see this result. Right. This is the last approach, which I'm going to talk about in this talk. Shown here is a catalytic cycle of single fission catalyst. What we employed here is a tetrasin diet, and this is a catalyst. This tetrasin diet can absorb one photon, and one of the tetrasin can be excited to single excited state. This tetrasin has very low triple energy, so this single excited state can dissociate into triplet, two triplet excited state of tetrasins. And these are still excited state. This excited state can be reductively quenched by decamethyl-ferrocin sacrifice electron donor to form this very unique bi-radical dianionic catalyst. This catalyst bears 2 electrons, so it can transport 2 electrons to Taiwanese reagent, two equivalent of Taiwanese reagent to form Schiff-3 radicals. This Schiff radical finally can be added to the alkene to form this trifluoromethylate product. Right. Sheehan was careful and hardworking students, so she managed to determine all the electrochemical potentials for photoinduced electron transfer. As you see here, this bi-radical dianionic catalytic intermediate has oxidation potential as negative as 1.15 volt versus SC, so it can transfer 2 electrons to Taiwanese reagent. And you can see that reduction potential of Taiwanese reagent is minus 0.91 volt versus SC, so the electron transfer to the catalyst to the Taiwanese reagent is thermodynamically possible. Right, this is good, but I have to say that what we still can't understand here is how this low band gap energy triplet excited state can generate this large gap by radical anion species. This is very puzzling to me. So we are still working on this mechanism. Nevertheless, we wanted to examine whether our catalytic system actually works or not. This tetrasin diet for the catalyst can absorb green LED, as you see here, because a large spectral overlap with green LED emission spectrums. And we examined the trifluoromethylation reaction of, we examined the trifluoromethylation ability of these catalytic systems. We added hexanols, Taiwanese reagent, and this tetrasin diet, a catalyst, decamethyl-ferrocin, potassium carbonate, which is a lot. And we shine the green LED light, and then we obtain this trifluoromethylated product. We determined the quantum yield of these reactions. The quantum yield is as large as 146%, which is greater than quantum yield of the single photon limit. So we believe that our catalytic system can be characterized as a one photon-induced two electron catalyst system. Right. So let me briefly summarize my talk. I have shown three approaches to maximize photoredox catalytic abilities. The first approach was based on the doublet radical anion as a key catalytic intermediate. And the second approach was based on the triple fusion, which is actually a photon conversion, and this photon conversion process can activate photoenzyme. The third topic was based on singular fission, which allows to access the quantum yield greater than 100%. Right. The first research was done by Dongyan, who does not appear in these photos. And second research was done by Dayun here. And third approach is currently done by Shihan. I'd like to thank Professor Youngmin Lee for helpful discussion, and Professors Eunjin Jo and Jung University, and Professor Jin Byung Park for examining the reactivities of our catalytic system. And lastly, I'd like to thank Professor Luis Campos and Columbia University for providing us the tetrasin diet. With that, I'd like to thank you, my previous current group members, and thank you for kind attentions.
Thank you for the very nice talk. Does anyone has any questions to Professor Youngmin You? Professor Youngmin Lee.
So I have two simple questions. Part one is, okay, for the reaction, actually, we need a lifetime of the more than 10 nanometers, right?
No, second.
So, yeah, second. Why do we need the femtosecond range and something picosecond range?
Oh, you're talking about first part of my talk. The reason why I employed femtosecond range absorption spectroscopy is that the radical excited state of radical anion is very short-lived. Its lifetime is less than actually several tens picosecond. It's very short-lived. So to enable to monitor the kinetics of the excited radical anion, we should employ the femtosecond laser. Okay, and right. And your second question was?
Second question is that your final chapters, you showed that the CF3 radically is generated, right? So why there is no the dimerization of the product?
Oh, dimerization of CF3 radicals. Okay, that's.
So that could be the very fast reaction because of radical coupling, right?
Yeah, of course. That's interesting questions. We need to think about it. I think that is the reason why we did not reach 200% quantum yield. Thank you.
Right, so if there is no questions, please thanks to Professor Youngmin You for the nice talk.
Thank you.
And then I'll toss the mic to Professor Seung-jae Lee and Won Woo-nam for the closing the symposium.
All right, the official talk is over, and thank you for being with us past 3 days. So before the closing remarks, one will announce one important thing. So please, Professor Nam, please. Yeah.
Yeah, so I think we all enjoyed this symposium. I came up here not to deliver a concluding remark, because Seung-jae, I think he prepared well for the concluding remark. But I want to also ask you about the BKCs. I think they should come up now. Yes, Well, as you can see, that this is the journal from Korean Chemical Society. So we call this is BKCS. And as I said, when I gave an opening remark, that I became that chief editor 2 years ago, and I put a lot of effort to compete with the JAX. So well, I can say that JAX is a little bit ahead from BKCS, but I think we can catch and may have a higher impact factor soon. But to do this, I need your support. So please, I will send an invitation letter when you return home to submit an original article or any review article or account. So please accept my invitation and please support this journal, not only for myself, but this is for the Chemical Society in Korea, and especially that some associate editors are in this room. So you support Bioinorganic Society. So Yun-Ho is associate editor handling bioinorganic chemistry, and this Seung-jae is just appointed as an associate editor to handle manuscript in biological chemistry. So please support this journal, and hope that you accept my invitation later. So thank you. So this is.
All right. We really appreciate the contribution of Professor Nam. He initially organized this symposium, and he trying to get a fund from Korean Academy of Science and Technology. So please give him a big hand. This will be the last time. So. Okay, thank you for being here with us, both on and offline, and I really appreciate your contribution to this symposium. Before my closing remarks, I have asked a few short comments from Professor Sonny Chen and Professor Carol Brand and Professor Siegel. So first, could you connect Sonny? Sonny, are you in the Zoom?
I'm in there.
Yep, Sonny, could you give us some comment to this young guy?
Okay. Do you hear me, first of all?
Yep, I can hear you.
All right, okay. Well, I would start by saying the old man is back. And thank you for inviting me to give a few closing remarks. All of this could have been done by Wen-Wan Mihi Lim, and Dr. Lee yourself. You could have done this.
Thank you.
But I get, the honor, at least to be the first one, not because I have any more wisdom than the three of you. Harry Gray would have said on an occasion like this that folks who have managed to make it past 80 and approaching 90 can show that they have greater enduring power. They could sit through the symposium from beginning to end, and as you know, I'm still here at the very end. I did miss yesterday because of medical reasons, so I apologize for that. With this said, let me first congratulate all the young people, the graduate students, postdocs, and the young assistant professors from Korea who are participating in the symposium in person and have been sitting through all the talks. You are not only learning science, but also acquiring the training and the skills to endure. It turns out motivation and endurance are two of the most important virtues to have if you are to succeed in science, and of course, to conduct a meaningful and rewarding life. Since I'm 85 plus, I have the data. So let's give them a hand.
Thank you.
Thank you.
Thank you, Sunny. Next, to a closing comment. Kara, please, could you?
All right, thank you, SJ, for inviting me to make a few comments. So thanks again, Mihi and SJ and Wanu, for bringing us here together. For many of us, this has been our first time back together at a symposium in person. And so that's just felt really great. It's been really exciting. But at the same time, we've been able to enjoy lectures from people all around the world, even if they could not make it here. So while the pandemic has been difficult, one thing we've learned is how to use technology to bring people together. And that's been, I think, really enriching. So I want to thank our wonderful technical team here who've done a great job putting this together. It's been such a professional job. The title of this symposium refers to bioinorganic chemistry in energy and medicine. And we've seen, in this symposium, so many different applications of bioinorganic chemistry, catalysis, medicine, energy. And you can really see how our field comes together to solve some of the most important and difficult problems in our society. And I think that we're able to do that because bioinorganic chemists are really Renaissance people. We can use a whole range of skills: synthesis, spectroscopy, physical chemistry, computations, biology, cellular biology. We use whatever it takes to answer interesting questions, and that positions us to solve difficult problems. And so I think it's the best field to be in. Of course, I'm biased, but I think that all of you here would agree. Finally, I just want to note that it was wonderful to see the presentations from the early career researchers here in this symposium. You all gave really great talks, and it made me feel confident that our field is in good hands, looking forward, looking to the future. So congratulations to all of you, and let's give them a hand. And just a final thanks again to our organizers and everyone who's made this symposium run so well. This includes, the microphone runners, and the students make sure that we don't get lost or eat the wrong food or anything like that. So thanks to everyone for all of your hard work. And now it's time to celebrate. Okay. Thank you.
Thank you, Carl. Thank you. Thank you so much. Okay, so the final closing comment will be by Professor Roland Siegel from Switzerland. Professor Siegel, are you ready?
Oh, yeah, it's on. Okay. So I can only join in and congratulating and thanking again everybody involved, especially Mihi Won-woo and Zhejiang. It was really great, and I'm really happy about your courage that you had, about half a year ago when you started organizing this at times when the corona numbers, at least in Europe, went through the sky. And especially under these circumstances, it's really great to be here, and it is my first on-site conference since 2.5 years. And this makes it really exciting. Also, especially the science, what we saw is great, and I think since my undergraduate days, I have never learned so much about electron transfer as in these past 2.5 days, because, as an RNA scientist, I avoid everything that has to do with electron transfer. It's simply toxic. But it's been great and very encouraging also for the future to see this interdisciplinary approach that we have in biological inorganic chemistry. And I just can repeat what Kara said. I mean, this has been, after 2.5 years of Zoom and Teams and Google Meet, you really brought technology for a hybrid meeting onto a new level. And this is really great. And so I'm really looking to the future, forward to the future. But I think still being on site is better. Because also here, what we experienced in Korea and Seoul is, aside from the science, food and drinks is also very important. And you also brought this to a new level. Anyway, looking to the future, I've heard that Won-woo convinced the government to build a new airport on Jeju Island. So with this, I'm really very happy and looking forward to the, as secretary of the ICBIC IOC, to the application for the ICBIC. And I'm looking forward to see especially the young generation there when we hopefully will be there. So thank you very much again and all the best.
Thank you, Olan. Thank you. Okay, we really appreciate these wonderful closing remarks, and thank you for being with us for these past 3 days. It was a really wonderful time in the field of bioinorganic chemistry. 35 speakers from Korea, Switzerland, France, Taiwan, China, Hong Kong, Japan, United States, and Germany have contributed to this symposium. Audiences and speakers had a chance to hear the latest advances in the area of catalysts, reaction mechanism, methods in biology, and medicine. The 3-day hybrid symposium has provided us with a valuable opportunity to come together as we emerge from the pandemic. The Bioinorganic Society in Korea first tried in 2020 online, and we then launched this symposium annually through both online and offline. I really appreciate the symposium secretaries, Junhyuk and Hyukjin. Are you guys still in here? I really appreciate that. They are not run away. And also local committees, Jae-hung, Yun-Ho, Youngmin, Ki-young, they brought these wonderful speakers. You guys are still here? Thank you so much. And one of the big contributor is coming from the Ewha Women's University. The location in here is inside of the Ewha Women's University. So the student and all the supporters, we really appreciate your help. And for 3 days, we really appreciate your time and efforts. Okay. And also the Kara and Roland said our technical team, and we upgraded and we opened a new era of the technical the Zoom conferences. So could you show us the technical team? So it's really the wonderful, and the quality of the symposium is totally changed because of us. Technical team, is it? Yeah. Could you zoom in? And finally, I really appreciate all of the support from Hallymon, the Korean Academy of Science and Technology, and our symposium supports, especially one officer from KAST, Kim Yun-Dae 선생님. She cannot do anything lasted a few weeks because of we asked so many things to her. So now we have a really good numbers of views and subscribe our symposium, because our symposium is totally recorded, and whenever you want, you can watch our symposium. So yeah. Okay, so I really appreciate the organizer, Mihi and Won-Hu, and without them, we cannot do that. So my appreciation again to all of the speakers who joined the symposium and the audiences in person, online and offline. Hope you continue to be well, and looking forward to seeing you in the near future. Thank you so much.